Good afternoon in Singapore, good morning in Norway and other places in Europe, and I would say good very early morning in Texas. Professor Lau is joining us from Texas, United States. Welcome to the fifth day of the Norway-Singapore Science Week. Last week, we were addressing the first of three thematic areas on sustainable urban development. Now we are into the second thematic area, which is on decarbonization. And specifically today, at this webinar, we will address the topic of carbon capture, utilization, and sequestration. My name is Per Kristalund, and I'm Science and Technology Counselor at the Norwegian Embassy in Singapore, or Innovation Norway. And I have the pleasure of giving the microphone over to today's session co-chairs. Professor Alessandro Romagnoli, which is Director at the Multi-Energy Systems and Grids at the Nanyang Technological University in Singapore, and to Professor Matteo Chiesa, who's a Group Leader for Renewable Energy at the Arctic University of Norway. So with that, I'd like to give the word over to the two Italian co-chairs. Welcome.
You are muted, Alessandro.
I was saying, do you want to say a few words while I share screen?
Yeah.
As an introduction? Yeah.
So we'll start. Alessandro will go through in more detail on about what's day to day. But compared to most of you, I'm probably the guy that is greenest in terms of experience with carbon capture and storage. And I wanted to share a couple of slides of the recent work of the reason why, despite having worked and having been in the periphery of carbon capture and storage, I've never been 100% convinced of the feasibility, and not from a technical point of view. So first of all, throughout the year, I started my career at Sintef, so I've been working quite a lot with carbon capture and storage related stuff, but again, not actively. And after moving to the Middle East, one of the things that I've been working on was trying to reduce the energy penalty of any carbon capture process, especially post-combustion, by hybridizing with solar thermal technology. And this is something that CSIRO and a former Singaporean colleague of yours was sort of promoting. Lately, it was still around 10 years ago when renewable, except for probably hydro, was not exactly as mature as it is now. But very recently, last year, we did a study, a quite intense study of energy return on energy invested of different technology. And we compare of different renewable technology with and without storage, and we compare with carbon capture. Again, carbon capture in this specific context, carbon capture and sequestration, is related to the energy sector. And with our surprise, well, we were not very surprised. We confirm our sort of doubts, but we saw that for energy application, the energy return, and you see on these scale bar, the energy return is better for renewable and solar, wind, or hydro. And the question is why? And there's been quite a lot of discussion, and this is what I hope we could somehow address throughout the meeting today. Is it because we need to find a value of this CO2? What does it mean having enhanced soil recovery as a possible utilization of it? Does it contradict the storage part? And I think these are all aspects that we will hear more about. But I think there is a pretty clear drive finding a value of these carbon or these CO2, let's put it like that, so that you can offset the energy penalty that otherwise you would have. And Here, the table that you see here is, for example, the installation basis, the projected versus the real installation that we have up to 2016. And you see that carbon capture and storage has lagged behind compared to other alternatives. So the floor is yours now, Alessandro.
Sorry, Alessandro, you have to unmute. I muted you.
Yeah, sorry. Yes. So thank you, Matteo, for the quick intro. I think this is something that probably we can further explore during this session. Quick introduction about myself. I'm actually an associate professor at NTU, Singapore, in the School of Mechanical and Aerospace Engineering. And similarly with Matteo, I'm not a carbon capture, storage, and utilization sort of expert. I'm more on energy efficiency into new energies. But of course, this topic on carbon capture is something that is of interest to me as well. So, I mean, I'm very happy to co-chair with Matteo this session. And for the speakers as well, I want to briefly highlight on how we're going to structure this session. So we will have a total of 8 presentations. And we will bundle this presentation in 2. So we will have 2 presentations, followed by each presentation lasting 15 minutes. And at the end of each pair of this presentation, we will have a 10 minutes Q&A sessions. And then we hope that towards the end, we will have a bit of time to have a general discussion and, amongst all the panelists. So for what it audience, for this webinar, you can throw questions to the speakers by raising your hands in the MS Teams chat or writing directly in the chat. And as I said to the speakers earlier on, I mean, I would be happy if the speakers can also interact directly with the audience. But in any case, Matteo and myself and Per Christa will try to also pick some of the good questions to throw to the speaker. So I think this is how I was going to arrange it. And in this way, we should be able to make it within the expected 3 hours. So without further ado, I mean, I would like to pass the floor to Professor Lao-Hon Chung, who is going to share a bit more on the Southern Light Carbon Capture Storage Initiative. Prof. Lao, I mean, floor is to you.
Do everyone see my screen?
Yes, we do. Thank you. And we hear you clearly as well. Thank you.
Okay, this is Professor Chung Lao from NUS. I'm in the Civil and Environmental Engineering Department at NUS and part of the Petroleum Engineering program here. I joined NUS about 4 years ago, and before that, I worked for Shell Oil Company for about 35 years. So I've been quite involved with the E&P business side and somewhat on the CCUS side with the Quest project in Canada. Today, I'm going to share with you what I call the Southern Lights CCS concept. It's a concept yet, it's not a project, but I've shared this with some of the people who may be considering to turning this into a project. Now, I borrowed the word Southern Lights because there's a Northern Light project, and probably Amy will talk about that. Amy is our second speaker. Southern in the sense that it is being applied to Southeast Asia. Okay. I will talk about the current CO2 emission in Southeast Asia, the big picture as of now, and what the Southern Lights CCS concept is all about, and some of the potential for CO2 storage in offshore aquifers in Southeast Asia, and also in particular in depleted gas reservoirs in Southeast Asia. Then I will conclude my presentation. In 2018, the total carbon CO2 emission from ASEAN countries is about 1.6 gigaton. And of this, the biggest emitter was Indonesia, about 650 megatons, and for million tons, sorry. And Singapore emits about 40 million tons per year as of 2018. Now, if you look at where those emissions come from, about 41% is from power, that means electricity generation and heating, 27% from all types of transportation, cars, planes, ship, and 21% from industry. Industry means all types of industry, refining, chemical processing, cement, steel, all this, and 10% from all other types of consumption. Now, but not all of the CO2 could be captured. Roughly about 20 to 30% of the total CO2 emitted can be captured. They're mostly from large stationary plants, power plants, or factories. So if you take that, roughly about 320 to 480 million tons of CO2 is capturable of 1.6 that we emit every year. Now, 1.6 is actually quite a big number. If we look at Singapore, since most of us are in Singapore here, Singapore's aspiration is to peak its production of CO2 to about 65 million tons per year by year 2030, 10 years from now. That means Singapore will allow CO2 to keep going up, okay, but the intensity should go down, and the emission would peak by 65 million tons 30. After that, Singapore would like to halve the emission to 33 million tons per year by 2050, which is only 20 years since 2030. And then Singapore would want to achieve net zero before the end of the century. Now that's a pretty tall order, okay? Achieving net zero somewhere after 2050, there's no set date yet, but as soon as possible. Almost every country in ASEAN has declared their CO2 emission goal and how much they want to reduce it. Now, but the message from these two slides is that bold actions need to be taken very soon, actually now, in order to achieve the net zero goal somewhere within the century. And most countries want to be net zero by 2050 or 2060. The latest is China. They come out and say they want to be net zero by 2060, which is 30 years from now. Looks like a long time, but actually it is not. In this slide, I've shown all the major CCS projects in the world. As you can see, they are concentrated in US and Canada, okay? And all of those are onshore projects. A lot of them are enhanced oil recovery projects, especially those in Texas. And there are many CCS projects in Europe. In Norway, we have the Snapper project, we have the Snøhvit project, and we are going to install the Northern Lights projects. But besides Norway, there are a number of projects which are either in operation or being planned. There are a few being planned in Middle East and some in China and a few in Australia. But as you can see, in Southeast Asia, where we are at, there's no CCS planned or in operations. And I think there's an urgent need to take action very soon. Now, what is the Southern Light concept? This concept is to take at least 1 million tons of CO2 from Singapore, probably from Jurong Island. Now, most of the CO2 that Singapore produces is low concentration CO2, but there is enough high concentration, meaning 95% plus concentration. There's enough pure highly concentrated CO2 that we can take from Jurong Island. We would like to ship it to a third country, to another country, probably by dedicated CO2 tanker, depending on which country, it could be anywhere from 250 kilometers to 1,200 kilometers. And then store it temporarily, most likely in the onshore facility, but it could be offshore for that matter. And then, depending on which host country, we would decide on whether we inject the CO2 into a saline aquifer, a depleted gas reservoir, or oil reservoir, or geothermal reservoir. Now, if it is a saline aquifer or depleted gas reservoir, those are just for permanent CO2 storage. If it is an oil reservoir, then we can do enhanced oil recovery to get some profit out of the project. For geothermal reservoir, it's not only just storage. There is a possibility that we could harness the heat from the geothermal reservoir by the injected CO2 or producing some of the CO2, and then use that heat energy to generate electricity, which actually is renewable energy. Okay, so this is the concept of CCS, of Southern Light in a nutshell. Now let's talk about saline aquifer first, because this is a well map, and if you look at the color actually represents the thickness of the sediment in the continental margins all around the world. And the blue are the major rivers in the world. So this map has been published about 2 years ago. And as you can see, if you go around all the continental margins of the world, there's no lack of sediment. And most of the sediment are actually water saturated. Okay, but there may or may not be enough sand to form an aquifer. But the fact is that the sediment thickness is anywhere from 500 meters all the way to 500 meters. So that means there's a lot of offshore sediment in the continental margin, which means the nearshore area, where there is a lot of sediment, and probably there's a lot of space for CO2 storage if we can find the aquifer within them. Now, our concept is slightly different from the Northern Light concept, which is to inject CO2 into a shallow water but deep saline aquifer. Our concept is actually injecting the CO2 into a deep water aquifer, deep water meaning over 600 meters, but relatively shallow buried depth. Now, when one injects CO2 into an aquifer, the mechanism of CO2 storage are several. One is, depending on the nature of this aquifer, you can have a closed aquifer where it's like a box, and therefore you have limited amount of space for CO2 storage. Or it could be an open system where the water could be displaced by the CO2 and the water could leak out into a different zone or into an aquifer. So depending on which type of aquifer you have, then the storage mechanism could be quite different. But there are several mechanisms. One is just basically CO2 displacing water and take up the pore space. And in that case, the CO2 density is very important. If you have a temperature and pressure condition where you have a dense phase CO2, then you can store a lot more CO2. The second mechanism is the solubility of the CO2 in the water. So some of the CO2 dissolves in the water under the high pressure, and that actually would be able to store the CO2. The third mechanism is the compressibility of the rock. Actually, the rock is somewhat compressible, and you can create some pore space. But the key is the reservoir temperature and pressure, because the CO2 density and solubility increases with decreasing temperature. And that's one of the motivations that we propose injecting CO2 into shallow buried depth, but deep water reservoirs. Okay, this is the diagram that explains what I meant. On the x-axis, we have the water depth in meters. And on the y-axis, actually, it is depth below sea floor, or you can say it is a stone thickness. Now, there are at least 3 offshore CO2 injection projects into saline aquifer, and they are all in Norway. Snapper is one, and Northfish is another one, and then Northern Lights. But they are injecting CO2 into shallow water, less than 600 meters deep water, but relatively deep aquifers. Our proposal is slightly different. The orange curve is the curve where we would have a CO2 hydrate stability zone. That is, this is the boundary of the zone. When the water depth in the equator, near the equatorial region, when the water depth is over 600 meters, there is a CO2 hydrate stability zone. That means there is a zone
Prof.
where
Lau,
you can form. Yes?
3 more minutes to go.
Thank you. And there's a zone where you can form CO2 hydrate as a solid. Now, so our suggestion is to inject CO2 into an aquifer, either straddling between the stability zone and below, or right below the stability zone. Okay, so this is the hydrate stability zone. This is the aquifer. We would like to inject CO2 into aquifer, which straddle the two zones, so that you can have CO2 being injected into the aquifer, but the CO2 rises, it forms a solid hydrate, which forms as an additional barrier to the flow of the CO2. We are doing research where we are looking at injection of CO2 into the hydrate stability zone, but we want to delay the formation of the solid hydrate so that we can increase the injectivity. So we have actually mapped the locations within Southeast Asia, and this will be published in the paper that we are going to publish in JPSC. Now, in terms of depleted gas reservoir, there are many in Southeast Asia, especially in the country of Indonesia and Malaysia. So depleted gas reservoir is another big storage potential. So our idea is to create a pan-ASEAN network for CO2 injection, form a public-private partnership to de-risk and incentivize the partners. We use a ship-based CO2 transport to the host country, and where we do the CO2 injection. And pretty much like the Northern Light project, this would be an open access project where another country could contribute CO2, and we would like to collaborate with other non-ASEAN partners. So ASEAN emitted about 1.6 gigatons of CO2 in 2018, and according to a previous study by the Asian Development Bank, ASEAN have at least 54 gigatons of CO2 storage, which is roughly enough for about over 100 years of CO2 emission for all of ASEAN. But our calculations actually show there's a lot more storage space, and mostly in deep water aquifers and also in depleted gas reservoirs. So we are proposing a Southern Light by shipping 1 million tons of CO2 from Singapore to a host country for permanent CO2 storage, most likely in the aquifer or depleted gas reservoir. And the project would involve a public-private partnership, intergovernmental coordination, and collaboration with international partners. So with this, I'd like to end my presentation. Thank you.
Thank you, Prof. Lau. Actually, it's on the clock, 15 minutes. So
all right.
Thank you so much. I would like to now invite Dr. Brunsvold from Sintef Energy Research, who will be talking about the Norwegian CCUS Research Center.
Okay, do you guys see my screen?
Yes, we do.
Okay, let me, I'm not sure what's happening here. Let's see, I'm gonna go here. Okay, I'm not sure if my camera is on too. Now I'm adjusting back quickly to my home office for a few moments. Okay, here we go. Thank you very much today for the introduction, and thank you for the interesting introduction presentation, both from the chairs and also learning about the Southern Lights project. So I'm happy to be here today. I hope I can give you a brief overview of one of Norway's largest R&D efforts on CCS, so the Norwegian CCS Research Center. Now, I guess for the group, it's probably not necessary now to go too far into the background of CCS. Obviously, we know we need some level of CCS to achieve the Paris Agreement. We need everything in our toolbox. And we also know that many industrial sectors cannot reach their climate goals without CCS. And indeed, if we're also going to become climate neutral or climate positive, carbon negative in the future, we as a globe will need net negative emissions, something that is just simply not possible without CCS. Now, before I jump in, I thought first, I guess I should say I am a senior research scientist at Sintef Energy Research. And the Sintef organization is one of Europe's largest independent research organizations here. We have, I have a few of my colleagues also presenting in this session today, so I thought I would just give a very short overview here. We have more than 2,000 employees from many different countries and over 3,500 customers around the world. You can see some more of our metrics here, but Sintef is a contract-based research organization, and we have a close collaboration just in general. We are kind of a spin-off organization of the Norwegian University of Science and Technology, NTNU, and so Sintef started back in 1950 and has celebrated recently our 70th anniversary. Over these decades, CCS has been an area of key focus for the Sintef NTNU platform here. This very busy slide here is just trying to illustrate that we work across many different types of projects in our strategic project portfolio. This is a non-extensive list of the projects over the last decades, but it shows examples of our industry clients, our collaborations with universities and other research organizations and governmental organizations around the world. And I must say that I'm impressed that Norway has invested in CCS research for the past 3 or 4 decades, I guess. Of course, you also heard about the actual CCS projects actually in operation since the mid-90s, but Norway has an active, let's say it's a research council funding program called Climate program. We also have a variety of other links to European CCS research projects. We also have this test center in Mongstad. Yeah, like I said, we have Sleipner, which has been storing CO2 safely for 25 years. And we also have Gassnova, which is kind of the cornerstone of CCS in Norway. It's state enterprise that manages the R&D interest, the test center in Mongstad, and the Norwegian full-scale CCS project, the Northern Lights project that you just heard about, which is now being called the Longship project to confuse things more. But I'll come back to that. So we also have a program in Norway, in the Research Council of Norway, called the FME program. So that's, FME is the Norwegian acronym, but it's Centers for Environmentally Friendly Energy Research. And NCCS, the Norwegian CCS Research Center, is funded under this program, which has been established to conduct concentrated, focused, and long-term research to solve specific challenges in the field. And NCCS is one of 8 centers that were granted funding back in 2016. So now we are headed into our kind of midterm evaluation timeframe, and so we are busy piecing together all of the interesting work we are doing and trying to put it into a story also of the potential value created for CCS in general and also CCS deployment in Norway and Europe and the world. We are funded 50% through the Norwegian state, and the rest are funding through our industry partnerships and research partnerships. But this kind of funding mechanism ensures pre-competitive competition and cooperation, among the partners. So our goal is to have the results open, of course, for all partners, but our primary goals are also to publish our work in the open literature, to educate students, PhD students, postdocs, masters, etc. So therefore, our focus kind of tends to be on low to mid TRL activities, but we also see this as an excellent springboard for further development of technologies as they move up the TRL. So we have a platform, a location for research industry to come together, and many ideas can also spin out of the center into higher TRL technology development. So with that, I'll go into a little bit about our vision. So this is a long vision here, but our goal is we believe that we can help fast track CCS deployment by focusing on R&D on the major barriers for CCS deployment that is identified within our demo and industry projects. And I know this is wordy, and also we heard in the opening is, what are these barriers and are they technical? We know that CCS has been deployed. It includes well understood technologies, and there are many successful large-scale integrated projects already in operation around the world. And we know that it's usually a cost issue. There are challenges with commercial and business incentives and regulations and the framework around those that, to ensure public acceptability, need to be better developed for large-scale deployment. However, what is the role then of technology R&D now, and why do we have a whole center on this? And are we able to communicate the need for R&D without distracting from the fact that CCS can be done now and should? So in NCCS, primarily a technical R&D research center, we focus our R&D efforts to overcome one or all or these barriers to deployment. So either reducing the costs of CCS, de-risking CCS, or scaling up CCS, or a combination of all three. And I'll come back to that in a second here, but maybe I'll stay here for a bit. I guess in NCCS, we conduct R&D along the whole CCS chain. So we have capture, activities, transport, storage, and the value chain. And like I said, we target these barriers. And so when I say reducing the costs, could also mean increasing the value, but it's like through improved methods, clever integration, improved processes, perhaps new technologies. When I say de-risk, I don't mean that CCS is super dangerous and we need to fix that. I mean more that we can improve safety, of course, we can tackle environmental aspects, we can reduce uncertainties, either in processes or financial de-risking through like reuse of infrastructure, et cetera. And finally, scaling up means everything from moving technologies up TRL to enabling large-scale CO2 storage or large-scale carbon-free power generation. But in general, NCCS aims to deliver just the scientific knowledge and technology solutions that can help play a role in unlocking future CCS, large-scale CCS deployment. So I'm going to skip that here. We do all of this in a comprehensive and diverse consortium of all of our partners here around the edges here. And in the middle, the blue circles are our 12 R&D tasks that, again, like I said, cover the entire value chain. And each task has what we call a task family, where our partners from all institutes in the center can come together, develop plans, and discuss results. So this list is changing almost every day as new partners are coming in. So we're really excited with the developments in Norway, especially with the full-scale project, which again I'm coming back to, is also creating and generating more interest in looking at R&D and the how to shape R&D now to improve the next phases of CCS, especially in Norway. NCCS is also closely linked to ExCEL, which is the European Carbon Capture and Storage Laboratory Infrastructure. And this is, maybe you've heard of it, but this is an open access laboratory network consisting of, I think it's almost 80 or more world-class research facilities for CCS across Europe. So it's a great way to use facilities across Europe and also get to know the research groups who are operating those facilities. Oops, okay. So once again, as a largely publicly funded center of excellence, we not only have to conduct industrially relevant R&D, we also have to let's say, deliver across all of these pillars. We have to maintain our research competitiveness by publishing our research in high-ranking journals. We have to educate our students and integrate them tightly into our research portfolio. Promoting innovation and trying to quantify the potential value created from the work, and of course, disseminating and communicating this impact. And just point you out that if you want to read anything about these 5 pillars and how we set up the center and some experiences from the first few years of operation, you can check out this article. I can also mention, after the talk just before me on the CO2 hydrates, I can say that our first Best Paper of the Year award from last year, we had in 2019, we awarded 2 Best Papers of the Year, and one of those was on demonstrating the potential of CO2 hydrate self-sealing. So that's kind of an interesting link, and you can also check out that paper on our website. Okay, so now back to the full-scale CCS project and this Northern Lights project. So you have heard that Norway plans to build the world's first industrial CCS project with an open access infrastructure. And the long-term ambition is to reach the climate goals in Norway and the EU in a cost-effective manner. And so now they are calling this project Longship. And Longship now includes capturing CO2 from the Norcem cement plant in Breivik in the southern part of Norway, near Oslo, and excuse me, and also Fortum's waste energy plant in Oslo, transporting the CO2 captured there via ship to an onshore terminal on the west coast of Norway. And then the CO2 will travel via pipeline for injection 10,000 feet under the sea at the Northern Lights project, which is the transport and storage part of Longship. So this is a collaboration here between Equinor, Total, and Shell. Now, there has been quite a lot of progress made recently on this because just last month, or I guess in September, the Norwegian government presented a funding proposal with significant public funding to develop the Norcem cement facility and the Northern Lights transport and storage infrastructure. Excuse me. They've also earmarked funding for, excuse me, for Fortum, for the waste energy plant. And they're busy trying to raise funds through other programs such as the Innovation Fund to kind of match the funding that is earmarked from the Norwegian state. So this is exciting developments, and we hope that this continues further. But it's at least it's a very, very important step further if we're going to not only reach the long-term goal, but also the short-term objectives of Longship, which are right here. So I already mentioned the long-term goal, but in the short term, they really believe that this open access, we believe that this open access project can help reach our long-term goal by demonstrating that CCS, just not as a necessarily commercial tool right now, but as a climate mitigation tool, can be implemented. We know how we can do it. Technically, regulations can be
Amy,
set up.
three more minutes to go.
I will hurry, and also commercial. So it's commercially, so we can show that CCS is safe. We know how to monitor and avoid emissions also at the capture site. So this is really, really promising. And what NCCS can do then again is to help tailor our R&D portfolio to make sure that this does not become a project that just ends, that it indeed reaches further, builds out. It's already the Northern Lights part of the project is oversized, so that additional CO2 sources that come in can be stored there. And also there's different scenarios developed here in this report where you can see that it really, Longship could indeed be a kickstart to what is needed, large-scale CCS deployment in Europe. Okay, so I will move first here back to NCCS and the link to the full-scale project. We will soon be releasing a memo on all of the tasks and the link to Longship. This is not ready to be presented yet because it hasn't been approved by our partnership, but I can say that as we develop our plans for the coming years, we really aim to be even a stronger research arm of Longship and other demonstration projects that come online. We are busy now mapping. This is just illustrating some of our selected innovations in NCCS. On the left-hand side, you see our TRL level, and here you have just very short descriptions. The idea to show here is that we are working in the TRL region of 2 to 6 or so, and we are developing further on how we can create even more industry uptake of the results that we have, and also how can we move some of these even further in either with partners in NCCS or outside of NCCS. So in this short talk today, I could all the examples here, but you are free to look at our website. We all have some of this described in our annual reports, and also we have a blog on the impact of NCCS research and innovations, where a few cases were assessed to try to quantify the potential value created of these new innovations. So I just encourage you to read this or check it out or ask us questions. Okay, so let's see, I think I might skip this kind of, but also I can just say that NCCS has also illustrated the potential opportunities for industrial and job, let's say, creation if CCS is implemented, and this is showing under different scenarios what this could mean for the job market in Norway. And also earlier this year, we came out with a kind of a popular science blog that debunked the myth that CO2 storage is risky or unsafe. And in this blog, we explained that CCS is a proven technology and that we have moved from theory to implementation decades ago, that it's a well understood, low risk process, and that we know how to do it. And also, since there's no shortage of storage space in Norway, we can carefully choose our storage sites and have the optimal storage location and solution. So I guess my time is running out, so I don't think I'll spend too much time here, but with CCS, we need to start now. We can't wait for the cost to come down. We have to deploy and do R&D simultaneously. That it's safe, we know how to do it. De-risking implies risk, but we need to communicate that it's safe and has been done already for decades, that it provides value, that it's expensive, but is it expensive compared to what? We show that we need CCS, and many other technologies have benefited from subsidies and many years of learning by doing. And R&D can help by reducing the costs, quantifying value, and optimizing performance. So with that, I think the whole all of NCCS, and here is the management team and all the task leaders. And I am happy to answer your questions either now or later if you want more information about our center. So thank you very much.
Thank you, Amy. Thank you so much for your presentation. Okay, so now we can open the floor for some questions. Matteo, you have a question? Yeah.
Question for Amy and for Professor Lau. I mean, both of you have given a very nice presentation, and actually it provides, we're ready to deploy. And Amy was explaining, okay, we need to create value or decrease the cost by creating value. But you never mentioned the word CO2 utilization. I mean, CO2 is not an enemy, is not, I mean, you can do many different stuff. Now, obviously, you are perfectly right that sequestering it provides a different input into the, so can you tell me something about it? And then the other thing is, how many more public funding projects do we need before we are ready? I mean, sorry, then if I have to, if I could just, with the same amount of money, I could put up renewable in the Northern Africa region and have all of Europe, electricity for all of Europe by renewable, and I wouldn't need any of the current gas. I mean, I understand that the process industry is different, but do you have an idea regarding that, or any answer, or any thoughts?
Yeah, should I answer first? Or I can
Please.
start with the first one on CCU. I do agree that there could very well be interesting opportunities there, and I think we'll hear more from Richard from Sintef about those type of things. But when it comes to the presentation that I gave on NCCS, the CCS funding in Norway typically to this date has not included the U part, and that is partly because it's been the climate program was specifically to make sure that CCS is a climate mitigation tool. So unless the U hasn't been LCA assessed to ensure permanent removal of CO2 or permanent storage of CO2, then it hasn't been included. So one could talk about what kind of strategic platform the Research Council should have there, but that is the reason why it's also not included in the FME, is because it's not seen to be a large-scale climate tool to help prevent climate change.
Yeah, let me chime in here. So the question is to choose between CCU or CCS. We need both, but if you compare the two type of technologies, the TRL level for CCS is actually higher than most CCU technologies. And so therefore for climate change initiative to remove gigatons of CO2 from the atmosphere, we need to install CCS right now while we are working to increase the TRL level of CCU. So I think we need to do both.
Yeah. And I agree that if we can use CCU and demonstrate the capture part and demonstrate, that we can reduce the costs of, let's say, CO2 capture, as long as we don't distract from the fact this is not a detour from large scale of CO2 that just needs to be stored. So we need both, but it shouldn't distract us from the main goal, is my opinion. So. Thank
you. So I can see hands being raised by Richard, Heyn, and then Per Krista. So Richard, maybe you want to say something? You want to unmute yourself?
Yeah, I will just simply comment regarding this myth that CCU needs to show long-term storage does not take into account the fact that CO2 CCU reduces the need for the combustion of fossil fuels, and that is its long-term effect. And I'll be saying more about that later.
I think you're the best to talk about that. Thanks.
Thank you. Per Krista, do you have a question from your side?
Yeah, if we have time for this, I'd like to address my questions on the chat. That is on the pricing of CO2 that is needed as the financial vehicle to do any of these activities, unless it's fully government subsidized. So we need to have a value on CO2, and that's, of course, that is the avoidance cost or avoidance credit for not releasing it to the atmosphere. So talking about the tax level or the CO2 market levels that is today, we're talking maybe optimistically $20, $30, $40 per ton. Would that be sufficient to actually drive this from a commercial point of view, or do we need to have an order of magnitude higher price for CO2? Maybe this goes both to Professor Lau and to Professor Brunsvold.
Amy, you want to start with that first?
I don't think that's enough. If that was enough, obviously we would have some place, right? So I don't know the details, for instance, in Norway, what the cost per ton CO2 is planned for, I don't know what they estimated actually for the Longship project. But of course we need, and the idea back to the topic of, do we need more publicly funded projects? I mean, I think one could argue that, maybe not, maybe yes, especially when it comes to the industrial sectors, because we can't just electrify cement production. So I think with CCS, we should, that's why I like Norway's idea of this open access infrastructure. They're focusing on developing a place for more than just this project, you know, that it could be a Kickstarter further, but I'm just a research scientist. So.
Yeah, so actually the cost of CCS for carbon avoidance is industry specific. So there's no one number. Some industry like steel is very expensive. Other industry like processing natural gas is actually cheaper. So it depends on the industry, because the CO2 concentration at the emission part is different for each industry. And also the shipment of CO2 to the nearby site is also different. So at least in the US context, they need at least $35 per ton. But that's probably just for the low cost industry. So if you want to decarbonize the hard to decarbonize industry like the steel, the cement, it'd be a lot more expensive. It could probably reach to $100 per ton. But in ASEAN, Singapore has only $5 per ton. They will increase, which is about $3 per ton. They will increase it to 30 Sing dollars by 2030, but that's still very small compared to what we need. So the problem with ASEAN is that besides Singapore, I think Malaysia is going to impose a carbon tax. They say they will. I have not seen that in the news yet. There's no other country with a carbon tax or carbon credit. So without that, it would be very difficult to incentivize industry to install CCS projects.
Thank you, Amy. Thank you, Prof. Lau. So for the sake of time, actually, I would rather move on. I can see some more hands being raised, but I would rather move on with the next presentation. Thank you, Amy. Thank you, Prof. Lau. So I would like to call Dr. Nanji Hadia from A-Star, who is going to talk about the EOR as driver for CCS in Southeast Asia. Dr. Nanji, the floor is for you. Yeah.
Thank you, Alessandro, for introduction. Very good afternoon to those sitting in Singapore. Very good morning to those sitting in Norway, and very good early morning to Prof. Lau. Thank you. I thank organizers for giving me an opportunity for this talk. And in this talk, I would like to actually focus on some of the key aspects why EOR can be a driver or can be a starting point or for CCUS activity in Southeast Asia. This is the outline I show. Basically, what is the energy mix currently is there in Southeast Asia? Why we need EOR, especially in Southeast Asia region, and how CCUS or CO2 EOR especially can become a driver or as a starting point for CCUS hub in Southeast Asia, and then I will conclude my talk. Now I would like to start with basically the demography of Southeast Asia, and if you look at the population of the region, as you can see on the magenta graph, that the population has been increased significantly over last 4 decades, and it is expected to grow by 20% in next 20-30 years. So what does this mean? This means that as population increases, energy demand goes up, and if you focus on energy mix, as we can see that over the years, the energy demand has increased overall, and the region has a very high dependency on fossil fuels. About 75% of the energy needs are coming from fossil fuels. So which is, and these are primary energy demands. And then as you increase the consumption of fossil fuels for your energy needs, then naturally the CO2 will go up. And if you look at the demand supply forecast, or the predictions, or the history of the fossil fuels, oil, natural gas, and coal, mainly. This is the outlook from.
Yeah, very quickly. There is a gray box appearing in your slides that is obstructing the view of the. Yeah, thank you so much.
Okay. So
thank you, Praveen, to pointing that one out.
Yeah, if you look at the Southeast Asia primary energy demand and supply for oil, natural gas, and coal, this is the latest outlook by International Energy Agency. And if you look at the oil, there's a worrying picture that in 2000, about 20 years ago, the demand was almost equal to the supply. But as the time goes, the gap is widening a lot. Coal, since Indonesia has a lot of coal resources, probably near next 20-30 years, coal might not be a problem, but high dependency on coal will again increase the climate problem. Natural gas for next 10-15 years should not be a problem, but as you go along, probably there will be a demand supply gap will widen. So what is so basically the bottom line is that by 2040 or by 2050, the Southeast Asia region may become a large net importer of oil and gas. And what does this mean? If with the current policies in place, or current government policies, the region's oil and gas bill may go up to $300 billion. So that is the bottom line. So with this increasing oil and gas demand or fossil fuel demand, as we can see here, that the CO2 emissions with the current policies in place, CO2 emissions for the region would drastically go up in next 20 years, maybe go up to by 200%. If actions, as Prof. Lau mentioned, if the actions haven't been started now, then it's a worrying picture for the region. So here we have a dual challenge basically. One challenge is how to meet rising energy demand and how to mitigate rising climate change problems. And especially for the region like Southeast Asia, which has very long coastal lines and coastal region, problems like rising sea levels is a major threat for the region. So that's where CO2 mitigation has become a crucial for the region. So what are the ways to basically for decarbonization? And there are various ways by which we can decarbonize the environment. And as per outlook by IEA, we can see here the contributions from different factors or different strategies coming. And of course, it's well known that efficiency improvement of the existing facilities or existing energy industry and implementing renewables, as Matteo stated earlier in his introductory slides. Efficiency and renewables would play a key role, definitely about 70 to 80%. But then there's a question that what is the TRL basically readiness level of implementing or technological viability of these technologies for the region. So of course CCUS is able to contribute 7%, but that gives us a good starting point, because as previous speakers have mentioned, CCUS is a well-known and well-established technology. So that, and if I go to my next slide, why CCUS could be a good starting point for the region? Because as Prof mentioned in his presentation, ample amount of storage capacity available in the region in terms of various, it could be saline aquifers, it could be depleted oil and gas fields, it could be for EOR, and one important point for the region is that this region has lots and lots of oil and gas activities for maybe decades. If you look at the Indonesian oil history, in one of the Indonesian oil field is more than 100 years old. So region is very extensive experience in oil and gas activities, and based on these activities and current knowledge of the fields and reservoirs, that can be leveraged quickly for quick action to mitigate climate change through CO2 CCUS and especially CO2 EOR, because region needs oil and the region needs to mitigate the carbon climate challenge. So that's where CO2 EOR becomes crucial for the region, I guess. And looking at the oil demand and oil supply gap widening, I think EOR is the only solution to the region if for incremental oil. CO2 EOR can be well placed in that particular regime of EOR. Just to highlight or just to give an idea, there was a publication a few years back where authors have kind of studied identified 127 fields in Indonesia, basically Sumatra region, and they've come up with a kind of a calculation that for next 20 years that about 660 million barrels of oil can be recovered through CO2 EOR, and which can store about quarter of gigaton. Now these of course these calculations are based on some assumptions, and because for some fields data are available, for some fields only part of the data available, so authors have made some assumptions. But what I would like to point out is that there's an ample opportunity available in the region. Of course, this is not only the case for the Indonesia, but same case in Vietnam also, and maybe in Malaysia, where lots of ample opportunity is available for CO2 EOR, and of course storage as well. So now, as we know, CO2 storage can happen in different formations. It could be saline formations where you identify the right saline aquifer and you just inject captured CO2. It could be injected into deep unminable coal seams. It could be used for EOR, and it could be used. It could be stored in depleted oil and gas reservoirs. These are well-known facts. And now, why CO2 EOR especially? Why I'm focusing on CO2 EOR? As I mentioned earlier, the rising demand and decreasing oil production for the region is a worry. So, mounting climate challenges that's where CO2 EOR can certainly fit to address or partly address some of these issues. And along with incremental oil recovery, CO2 can be safely stored almost permanently in the reservoir, which can boost oil production. And some of the recent publications showed that CO2 EOR is able to supply net zero or negative carbon oil, by which you can decarbonize the region. And over the years, as we can see that see from this bar chart, that number of EOR projects is increasing, but 2000 onwards, CO2 activities have gone up quite significantly, and it is expected to grow in the future. This is because people have, industry is realizing the effect of storage as well, which is quite substantial as far as EOR is concerned. So, and it is expected that CO2 incremental oil recovery by CO2 will also go up in the future. And as you can see, it has steadily grown up, and it is expected to grow up because the technology will develop with the help of more efficient technologies, more number of projects being taken up worldwide. It is expected to go up.
3 more minutes to go.
Thanks, Alessandro, for that. Now, as you can see, that over the last 5-6 years, Asia is also picking up to take up CO2 EOR projects. Previously, Northern America was kind of CO2 EOR was well established, but now Asia region also picking up, and recently Indonesia and India also planning a CCUS project. And I think Indonesia is going to try CCUS pilot in one of their fields. So what are the key technologies? These are well-known facts. Miscible CO2 EOR is one of the technologies where we inject CO2 in an oil reservoir. CO2 gets miscible with the oil, and then basically decreases the viscosity of the oil, interfacial tension, and then oil simply moves through the production well. Now, this is a well-known and well-established technique. But when we deal with the gas for any EOR project, we face sweep efficiency issues because of low density and low viscosity, which means early breakthrough of the gas, low recovery, and hence less CO2 storage. So how to mitigate these issues? And of course, a trapping mechanism, as far as a safe CO2 storage is concerned, I think the mechanisms of CO2 storage is such that it can provide a very safe storage, unless and until unfortunately on unfortunate ground you may have very huge tectonic activities. I think it is a permanent storage through different mechanisms like dissolution trapping, then structural trapping, mineral trapping. So these are already well known and well established facts. The current research trends. So basically, the left-hand side is the conventional continuous CO2 injection gas, where we face problems of less efficiency, less CO2 stored. Then there is a kind of well-established technique called water alternate gas injection, which will improve the sweep. As you can see now, you can the orange region is decreased, but there's a trend now going on which is called surfactant alternate gas flooding, or called foam flooding, which can really help displace oil quite efficiently. And as you sweep more oil, as the sweep efficiency is more, as the foam is able to contact more and more reservoir, more CO2 is stored. And these are some of the trends available in the literature to increase the storage efficiency of the reservoirs. So finally, I would like to say what are the opportunities or challenges in the region as far as CCUS is concerned. The opportunities are like we have ample CO2 storage capacity in the region. extensive oil and gas experience in the region available, which can be tapped for CCUS, for development of CCUS. The geographic location is a compact region. Prior knowledge of some pipeline networks, interstate pipeline network is available. In case
Nanji, time is over. Please go to the conclusions. Thanks.
This will be my last slide. Yeah.
Thank you.
But the challenge is that incentivizing CCUS would be critical. Intergovernmental cooperations and international helpers, basically, like in terms of technical knowledge sharing and etc., would be very, very useful to establish Southeast Asia as a CCUS hub. Yeah. So as Prof mentions, implementing CO2 EOR will buy some time to establish newer technologies like renewables and efficiency. So yeah, with this, I'd like to conclude my talk. Thank you for your attention.
Okay, thank you so much. Thank you so much for your presentation. So I would like to move into the next presentation given by Dr. Alv-Arne Grimstad from Sintef Industry. The title of the presentation is EOR CCS Research Activities in Norway. So Dr. Grimstad, yes, the floor is yours.
Thank you. Can you hear me well?
Yes, we do.
Yes. Very good. I think I turned my camera on also. So good morning or good afternoon, whichever suits best. My name is Alv-Arne Grimstad. I'm a senior research scientist at Sintef Industry in Trondheim. I work in the petroleum department of this institute in the research group for applied geosciences, which also has a reservoir technology subgroup. And I have worked on CO2 storage projects since I started in Sintef back in 2005. So I will give you a talk on the EOR and CCS research activities in Norway with a focus on the activities at NTNU and Sintef in Trondheim on the CO2 EOR and CO2 storage topics. So in this talk, I will present the research groups working on topics of CO2 EOR and CO2 storage. I will present an overview of our research facilities and the research focus in the past and ongoing projects. I will also briefly at the end introduce a new Gemini Center. This is an NTNU Sintef Virtual Center on the CO2 EOR and storage topic. This center was started now in 2020. So the research groups working on CO2 EOR and storage topics can be found in the NTNU Department of Geosciences and Petroleum and in Sintef Industries Department of Petroleum. These departments are almost co-located physically at the southern end of the university campus. And the opportunities for cooperation and co-supervision of students are good. Students can in this way have access to world-class laboratories and instruments and can be part of the research on scientific problems with industrial relevance. NTNU's Department of Geoscience and Petroleum has a staff of about 200 people and covers scientific disciplines on mineral resources, oil and gas, and also engineering geology. The Reservoir Engineering and Petrophysics group in this institute covers the topics most relevant for CO2 EOR and storage. And this has 7 main scientific staff and about 13 PhDs, postdocs, and researchers. Sintef Industries Department of Petroleum has a total staff of about 60, and in the past years the amount or the fraction of CCS related project has increased steadily and is now a significant part of the total project portfolio. The Applied Geoscience group where I work can be further divided into reservoir technology, basin modeling, and geophysics groups with a scientific staff of about 20. We have a formation physics group, research group, also with scientific staff of about 20, working on rock mechanics, and I will come back to that. And we also have a drilling and well technology group with CCS-related research, scientific staff about 10. So the facilities we have for CCS research and both laboratories and in software, we have access to a wide range of experimental facilities and modeling software that can be used to tackle the scientific challenges of storage and of CCS. Much of the facilities and software were initially, of course, developed for use in petroleum exploration and production. But as we know, the technologies for CO2 EOR and for safe CO2 storage are much the same as for petroleum operations. There's a rough division between NTNU and Sintef in that the facilities at NTNU are more directed towards education and basic research, while facilities at Sintef are directed towards contract research for industry. But we find many examples of crossover or overlap in this, particularly within CCS, which is a fairly new research area. And we can see that the funding is still mostly public and the research topics have a significant component of basic research, also in the Sintef. This may be changing now when we are hopefully finally entering the demonstration phase of large-scale CCS deployment. Laboratories of special interest for the CO2 EOR and storage are the Reservoir Technology Laboratory, the Rock Mechanics Laboratory, a Well Integrity Laboratory, CO2 Field Laboratory, and also the Computed Tomograph Laboratory we are installing now. The Reservoir Technology Laboratory has setups for steady state and unsteady state core flooding, in situ saturation measurement. And the Associated Fluid Laboratory can measure relevant PVT properties of the reservoir fluids, including CO2. And we can also measure interfacial tension of reservoir fluid systems down to values relevant for near critical systems or surfactant flooding systems. The Rock Mechanics Laboratory can measure strength of reservoir rock and cap rock in uniaxial or triaxial load cells. And we can study borehole stability and sand migration and observe how shale creep can be part of the plugging and abandonment strategy for wells. Tests in the load cells can be done with a range of pore pressure conditions and combined with measurements of acoustic velocities, resistivity, acoustic emissions, or permeability. In the Well Integrity Laboratory, we do tests of cement bonding strength in various situations, study the quality of cementing operations, investigate methods for well plugging and leakage remediation. We also investigate injectivity as impairment for CO2 injection operations, and study the impact of CO2 exposure of cement, reservoir rock, and cap rock. And we can do tests that include thermal cycling, which is relevant if you want to inject CO2 batch-wise for ships, for instance. Recently, we opened a CO2 field laboratory near Oslo in Norway. And here we can test novel monitoring methods for CO2 storage. The site is located at the ridge of glacial and post-glacial sediments in an abandoned part of a sand and gravel quarry. And here we can observe the response to brine and CO2 injection at 65-meter depth, using a range of instrumentation installed behind casing in 4 monitoring wells around a central injection well. The first campaign here was conducted in last year in 2019 as part of the PREACT research project. The coming year, we will be installing a new industrial micro-CT with options for imaging of samples of a range of different sizes, combined with multi-phase flow and acoustic and impedance measurements. And this CT will be used in combination with other laboratories, also with the Well Integrity Laboratory, with a special X-ray transparent pressure vessels. Software facilities at NTNU and Sintef includes both industry-leading commercial software for exploration and reservoir engineering, as well as in-house developed software for geological and petroleum system modeling, and tools for seismic inversion. Popular open source tools such as the MATLAB Reservoir Simulation Toolbox and OPM Flow are also used in combination with in-house software. The project portfolio for CO2 EUR and storage in Sintef can be traced back at least to a project in 1987, where CO2 EUR in combination with power production was proposed. The suggested technical solution was a floating power plant with oxy-fuel combustion and CO2 separation, where power was exported to shore and CO2 was used for enhanced oil recovery. In the years following 1987 saw many nationally funded and EU projects with both CO2 EUR and CO2 storage topics, often combining these. And the argument for combination of EUR and CO2 storage is that CO2 in the amounts relevant for most EUR projects must be sourced either from power production or from industry. There are a few CO2 rich fields in the North Sea, but they will not be enough for large-scale implementation of CO2 EUR. So if CO2 is recirculated after breakthrough in the EUR operations, the need for fresh CO2 at each oil field will be in decline after a few years. But committing to the capital cost of CO2 capture at the industrial source require time horizons of decades. And to reconcile these two, the proposed solution was to operate saline aquifer storage sites in combination with the CO2 EUR operations. And then you can inject CO2 not needed anymore for the EUR operation in the aquifer stores. Large-scale deployment of CO2 EUR on the Norwegian continental shelf was explored first in a project in the year 2002-2003. In this study, we proposed transport in pipelines from the continental Europe or from the UK, with calculated need for about 70 million tons of CO2 per year for the CO2 EUR operations. And this was then proposed to be used in, I think, 23 Norwegian oil fields that had been water flooded and would be good candidates for CO2 EUR. The study was also later extended to the UK sector of the North Sea, as shown in the illustration in top right, where all the yellow dots are CO2 EUR fields. At this time, the startup was proposed to be year 2013. Of course, this date passed without any Norwegian continental shelf CO2 EUR operations. As the fields now enter tail production, the window of opportunity is closing. However, much of the additional oil that could be produced with CO2 injection will still be there, even at this time. So the technical opportunity is still there, but you could say that costing the full CO2 EUR operation on only the remaining oil now is becoming more and more challenging. From about year 2010 or 2010, we can say that the research project portfolio in Norway has had more focus on larger projects that encompass the full CCS chain. Storage research topics in this project has still been both EUR and saline aquifer storage, and with both laboratory and simulation work. We also developed the CO2 field laboratory in this period for doing monitoring research. The last decade, we have seen more involvement from other subsurface research groups in Sintef, and CO2-related topics are now found in all research groups. Recent project has been the big centers, such as Big CCS and the current NCCS, and many national funded projects have been run, some as spin-off of the big centers. Safe CO2 storage can be said to be a proven technology, and CO2 EUR has been demonstrated onshore elsewhere in the world. The Norwegian full chain demonstration project coming up now is initiating the next step of CCS implementation. There are, however, still open research questions, and we focus on the topics shown here, improvement of predictions or reduction of risk of the storage performance.
3 more minutes to go.
Okay, so we improve site characterization methods, looking at how to use legacy well or make sure they are not leaking. Monitoring of injected CO2 is a large research topic. They need to be accurate and reliable, and you need to be able to implement early warning systems for CO2 storage misbehavior. And also storage in depleted oil and gas fields is an important topic coming up. So these research topics are then in the different research groups on long-term behavior, trap filling, fault behavior, leakage across faults, CO2 EOR, and also mobility control for CO2. It's an interesting topic which will increase the storage capacity or increase the efficiency of CO2 EOR. Geomechanical topics are fault initiation or fracture initiation and growth, particularly around pre-existing faults. Microseismic emissions, fracturation and settling mechanisms, cement bonding to casing or reservoir or caprock, which is done in our laboratory. We have for the well integrity, looking up the experience with CO2 injection wells around the world, looking at fluid flow in annular fractures in and around wells, and the thermal effect of cycling, precipitates, etc. For the monitoring, looking at integration of different geophysical monitoring methods in joint inversion, advanced acquisition methods such as fiber optic methods, and extraction of pressure and saturation information from remote monitoring data. These are all important topics and can be found in the existing project portfolio now and on possibly and hopefully in future projects also. So I will round off with the new Gemini Center for CO2 EOR and CO2 storage called CCUS. Not really sure how to pronounce that in English. The participating groups here are the Sintef Applied Geoscience Group and the NTNU's Reservoir Engineering and Petrophysics groups. The motivation is based on the ambitious climate targets for Norwegian oil and gas industry and the government and also other industries in Norway. And it's hard to see that these ambitions can be met without technologies like CO2 storage and CO2 EOR. So we see the need for increased focus on education for the engineers and scientists needed for actually pulling this off. The vision is to develop knowledge and provide education on CO2 EOR and storage, enabling optimal utilization of oil and gas resources while lowering CO2 emissions from industry and power production. And the goal is also to strengthen existing cooperation between research groups at Sintef and NTNU. And the education part of this center will reevaluate the study program, try to increase the uptake of master students in the relevant topics for this center, develop new teaching programs, and focus on problem and project-based learning. For more information on this center, you can contact either me, Alv-Arne Grimstad, or NTNU's Ashkan Johan Bani Kaparoki. And there is a web page in progress where you also can find more information after a little while now. Thank you very much for listening.
Okay, thank you so much, Dr. Grimstad, for your presentation. So we're running a bit late, but we have 5 minutes for Q&A. Any questions from the floor? Actually, during the presentation from Dr. Hadia, there was a question raised by Richard that then eventually also sparked a bit of a debate in the chat. Maybe I can throw that to Dr. Hadia again. I mean, the question was, why should the EOR be considered a climate mitigation technology?
Well, yeah, that's definitely a valid question. Well, CO2 EOR, there are publications which say that CO2 EOR could be carbon negative depending on technology that is used. I mean, how much CO2? Of course, there is a question like if you generate 1 barrel of oil by using some amount of CO2, will that 1 barrel of oil emit more CO2 rather than what is injected? So here, as far as CO2 EOR is concerned, the first and foremost point for climate, it is not the only tool. The point that I want to highlight, as I think Prof. Lau also mentioned earlier, that it is not the only tool, especially for the region. Why CO2 EOR could be a focus is because it will help mitigate some of the climate issues, as well as it will buy some time for the region to focus on more advanced technologies like renewables and efficiency improvements, for which TRL levels are quite low at this stage. So that was, and yeah, life cycle always depends on what boundaries you choose. So if you choose like gate to grave boundary, it could be carbon negative. But if you choose a cradle to grave boundary, it could be net zero, or it could be positive.
Thank you. Any other take on this aspect?
It is a paradox, you could say, that the more efficient the EOR operation is, the less climate friendly, or the less, or the more negative or the positive the total CO2 balance will be, or the more net emission you have. But so it's a balance of the operator that wants to use as little CO2 for the extra oil as possible, and you'd say the society as a whole that want to inject as much CO2 as possible into the oil fields to store the CO2. So the government would perhaps push for injecting CO2 into the far tail end of the project, while the industry or the oil and gas operator would want to terminate rather quickly after the CO2 breakthrough.
Thank you. Any other queries from the floor, from the audience?
Well, let me comment. In the absence of a carbon tax, this Prof. Lau, CO2 EOR is one of the few ways to make the CCS project positive in terms of profit. Because if you inject CO2 into the reservoir for EOR, you generate profit oil, and that pays for the CO2 mitigation. So in that sense, it is a carbon. Indeed, it is a CO2 mitigation project.
Richard, please. Yes, please.
But that only then has to take into account that the amount of CO2 you put into the oil field is greater than the amount of CO2 that is produced from the oil that is recovered. And if that's not always the case, then it is not a mitigation technology, regardless of if it's a profit or not.
Well, then you're taking the perception that we don't need any more oil, which is not true. If you look at the whole decarbonization plan, it would take quite a while before the world does not need fossil fuels. So in the process, if we could produce fossil fuel with less CO2 usage, that is a positive thing for the climate.
Yeah, but we need to we need to be carbon negative. We can't continue emitting CO2, and the only way that we're really going to solve this issue is if we decouple society's dependency on fossil fuels. That's the only way. That's the only way we solve this issue in the long term.
In the long term, yes, but the time issue is urgent. Okay, if there's not even enough renewable energy to decarbonize the power sector, let alone the transport and the industry sector. So in the meantime, we cannot wait until we have enough renewable energy to decarbonize the transport and the energy sectors. Therefore, we need to do CCS.
I'm not saying anything about CCS.
Well,
my only point is that is that EOR is not necessarily always CCS.
Yeah. And
Wow.
this, Professor Lau and Richard, I think the fact that we are having this discussion, it means that there are some unclear and gray zone in terms of when you can consider this really a way to get rid of CO2 or not. And the fact that we are having this discussion and we are all interested in this field implies that it's not a black and white type of story. And this is what I think Richard was trying to say.
Well, I would like to highlight is, let us say, even if it is carbon positive, let's say you inject 100 tons of CO2 and maybe produce some oil, and that oil will let's say emit 110 tons of CO2, but the net CO2 emission would be 10 tons. So that way, basically, we will be able to decrease the intensity of the carbonization of the atmosphere. If you don't implement CC, let us say you generate oil without CO2 EOR, 100 barrel of oil, which emits maybe 500 tons of CO2. But out of that 500 tons of CO2 produced, if you re-inject back 400 tons, then the intensity of the carbonization of the atmosphere is going to reduce, right? Or the rate of carbonization of the and that is also an advantage, because that will buy you some time. As I said, CO2 EOR or CCUS is not the only technology. Okay, renewables, efficiency improvements have a very major role to play, about 75 to 80%, as I mentioned earlier in the graph. But what CO2 EOR or CCUS will help is that it will decrease the intensity of the carbonization overall.
Yeah. Per Krista, you wanted to comment on this?
Yeah, I'm just thinking that Nanji's logic here is that you produce oil with the lower carbon intensity because you re-inject the CO2. The point is that you wouldn't be able to produce this oil without CO2 injection. So this oil is stranded, and that's where it's supposed to be, perhaps from a climate point of view. So you are increasing the total oil emission the oil production if you do EOR. But I think it was someone's maybe Alv-Arne's argument that the poorer the projects are, the better it is for the CO2 deposition, perhaps. But there is a break even somewhere, and that also a cost element into that. So that break even, I think, is 2 barrels of oil produced per ton of CO2 that you inject. If it's poorer than that, then it's a carbon negative. Above that, it's carbon positive. And then from there, you can actually assess what is the value of that CO2, because it's the value of 2 barrels of oil, which is what, 2 times $50, $100.
Yeah. And Christian and Nanji, sorry, Adam was.
Yeah, I think maybe Adam, you want to add something?
Yeah, just sorry, one thing. I appreciate this discussion and thank you, Richard, for raising this issue. And I appreciate what you're really trying to say, which is, look, let's focus on other means to decarbonize the world. But I just want to hammer home what I'm hearing both Nanji and Prof. Lau saying. Imagine you're producing hydrocarbons in one location, and you're doing CCS in a different location. And the issue is the amount of hydrocarbons that you have to produce is purely a function of the demand in the world. And the demand in the world, assuming it's not going to change in an instant, by combining the CCS with the production, you're basically able to get some synergy, some efficiencies. So you're using a little bit less energy to produce the hydrocarbon. That's another way of looking at it. And so you're sequestering as much CO2 as before. Meanwhile, you're producing the oil that you're going to have to produce somewhere anyway with less energy. And that's the concept behind the fact that maybe it's really beneficial. So that's it.
Thank you. Matteo, you want to give a last comment? Then we move into the next presentation.
Yeah. I think I agree in that time in that. But then we heard from Professor Lau earlier. The cheapest CO2 that you get from the energy sector. Okay, and actually the energy sector there is an alternative. So yes, inject the CO2 that you have extracted from difficult processes that you cannot substitute, and then substitute the energy sector with available technology that allow. So this is another type of argument in the equation of which kind of CO2 you are emitting or you are injecting, because hydrocarbon poorly used for the energy sector, we have an alternative. We have alternative. It's just a matter of how fast do we want to implement that alternative.
Okay. Okay, thank you, Matteo. I mean, thank you, everybody. I'm sorry I have to stop this conversation here. We need to move on for the sake of the schedule of this webinar. So I would like to invite Dr. Usadi from the ExxonMobil Energy Center in Singapore, who will be talking about CCS, R&D, and the dual challenge. Adam,
thank you very much. Can you see my screen,
yeah.
the slide? I'm trying. Great.
Very good.
So
very
yes,
good. Yeah.
Adam, yeah.
Thanks. So thank you very much. Thank you, Per Christer and Alessandro, for inviting me to talk about ExxonMobil's R&D perspective on CCUS. I appreciate the discussion. This is a great selection of talks. They're kind of all dancing. We're all dancing around each other, so it's perfect. That's great. I'm a computational physicist. I'm from our R&D. I moved here last year from New Jersey. I'm here primarily to work with the Singapore Energy Center, which was jointly founded by NUS and NTU almost exactly 2 years ago. Actually, it was during CU 2018, and ExxonMobil is a founding member. So I'm going to sort of try to run through quickly. Does the world need CCS to attain a 2C or even a 1.5C, meaning 450 ppm by the end of the century? And I think the answer is yes. I appreciate Matteo's questions, and I don't think it's a slam dunk. But let me just show you some data. This is from ExxonMobil's Energy Outlook. And you can use modeling tools to sort of explore what pathways can to get most quickly. And I'm a modeler, so I know models are all wrong, but some are useful. I appreciate that. But Stanford brought together a lot of the energy systems modeling groups that contribute to the IPCC, and they brought them to the EMS Energy Modeling Forum 27. They basically said, simulate for the next, to the end of the century, business as usual, and then simulate with a constraint to get to 450 ppm by the end of the century. These are all separate models. Now, the numbers here, these lines are like 13 different models. I think there were more than that. They're all different groups. They're from around the world. The models all have different assumptions, different methodologies, and so on. Now, the top, is the business as usual. And I want to point out, so when they were all asked to constrain to reach 450 ppm by the end of the century, look how quickly we need to decarbonize. It's dramatic. And look, importantly, like most of the models need negative emissions really soon through the end of the century. And I think this is the case for CCS. Now, what's in these models and how do I show this and so on? Well, if you take a slice at 2040 and you just look at all the different energy sources contributing to the demands that's anticipated by these models, the different colors, different energy sources, so oil, gas, coal, bio, nuke, renewables, and so on, they're all over the place. So these, this reflects the fact they all have different assumptions, but they all require CCS. And a big chunk of the CCS is with bioenergy, BECCS. And let's just be real about what's negative. The only things that I know of at scale that are negative are BECCS, bioenergy, biomass gasification plus CCS make hydrogen, or DAC, direct air capture. They're all tough. None of them are commercial now, but this is what these models tell us we need. ExxonMobil has a long history of working in CCS. It's actually the largest capture of CO2 with a working interest in more than a fifth of the world's capacity. And now with Gorgon, we actually capture about 9 million tons of CO2 per year. We've been doing it since the 1970s. CO2 capture is usually the most expensive part of CCUS, not always actually, but it's usually. So, and that depends on the concentration of the CO2 and the, other things like pressures and temperatures and contaminants and so on. The lower, in general, lower concentration and lower pressure, the harder it is to separate the CO2 from other gases, mostly nitrogen. Today, technology exists, and I think you've heard this from all the speakers, to commercially do CCS. But for low concentrations in particular, the processes are complex, costly, and they require additional power. So our R&D is focused primarily on the low concentration CO2, notionally about 30% or something like that. So I have like a heuristic conceptual framework to categorize the R&D thrust. It's not exhaustive and it's not really a perfect description, so please don't nitpick it too much, but I think it's useful. And one thing is we think of materials, and we think of it in terms of liquids, solids, and then fuel cells, which is kind of an odd mix. But on the liquid side, R&D on novel amines. On the solid side, solids like MOFs, and fuel cells, carbonate fuel cells is the focus. On contactors, meaning you've got this flue stream, it's got some concentration of CO2. You need some approach to allow at the molecular level of CO2 to bind to some amine or something like that. So that's what the contactors are. And in the case of liquids, it's towers, rotary beds, packed beds for solids, or it's the fuel cell stack and the fuel cell concept. And then finally in processes, and this is basically for the regen step, because you often have to do regenerate so you can save your materials. And then finally, it's what you do with the CO2. And we believe, and I think everyone here would agree, let's try everything, and work all problems at once if we can. But by far, we believe the biggest opportunity for large-scale CO2 sequestration is sequestering under the ground. You could sequester as a solid, or you could convert it into fuels or chemicals. In addition to our own R&D, which I'll talk about a little bit more with Singapore, but we have collaborations with a variety of companies and ventures and universities. And so we're evaluating right now the use of a fuel cell, a carbonate fuel cell for CCS in our Rotterdam refinery. We publicly talked about it and so on, so you may have seen some notice, and we published papers in peer-reviewed journal articles. But more broadly, we're working with many third parties on various low carbon solutions. For example, we're looking at MOFs with Mosaic, which is an offshoot of UC Berkeley. We're working with Georgia Tech on next generation processes. And in the case of Singapore, the Singapore Energy Center for us is one of 5 energy centers. It includes MIT, Stanford, Princeton, and UT, as well as the US national labs. We're working broadly with NREL and NETL on a variety of processes and technologies. Let me just give you a few examples of what we're doing with the Singapore Energy Center, just to give a flavor. Some of the work, the way the Energy Center is run, it's like MITI, which is that some of the stuff is collaborative with the industry partners, some of it's not, some of it's more like consortia. So these are examples of CO2 capture projects which are consortia, they're not collaborative. And there are 3 examples. I mean, membranes for CO2 separation in methane reforming, kind of syngas. There's the middle one here is kind of interesting. It's combining the need to do CO2 capture with trying to find a use for the fly bottom ash of waste to energy facilities and the brine left over from desalination. That's pretty cool, because if you could solve 3 grand challenges for Singapore at once, that would be pretty neat. And then there's work going on in Singapore as well on MOFs and looking at basically finding water resistant MOFs for CO2 capture. These projects are examples of projects that we're doing collaboratively, where we've got researchers from ExxonMobil, primarily in our New Jersey lab, although some of them are in Houston, with researchers at NUS and NTU. The first one is on COFs. COFs are covalent organic frameworks. They're like MOFs, but instead of metals, you just have covalent bonds and you just have lighter elements. We're working on synthesizing hierarchical, at the molecular level, hierarchical porosity in these structures, so that when you're actually pushing these high throughput flue streams through, they can contact the absorbing material, in an efficient manner. We're working with Praveen Linga about hydrates. I'll let him talk about that much more, eloquently than myself, but we're pretty excited about that project. And then we are working on a regional sequestration screening study like that Prof. Lau alluded to. I'll talk about that in a little bit more detail now. So this is a collaboration between ExxonMobil and three different groups, three different professors and their postdocs and graduate students at NUS, including the Energy Studies Institute and the Global CCS Institute, GCCSI, which is out of Australia. It's an ongoing study. It hasn't published yet. We expect to be able to, first half of next year. And so what is the focus? It's looking at sequestration. So there we've compiled data from several thousand existing oil and gas fields. We've applied a criteria, like I think I've seen discussed earlier, where we're looking for, subsurface reservoirs that are depleted oil and gas fields that are greater than 1 kilometer. If it's offshore, we're looking for ones that are pretty shallow water, less than 100 meters, so the well costs would not be expensive. We're focused on large fields, so they can support multiple years of injection. And basically using this criteria, we filter down and we have about 150 high quality fields. And then when we applied the methodology developed by the USGS, US Geological Survey, we compute the amount of CO2 that can be stored, including EOR. We actually looked both at EOR and just pure sequestration. And then the confidence of this data is pretty good because this is depleted oil and gas fields. We are now working on the saline formations or aquifers. That is a separate, but today I'm only going to show you the results from the depleted oil and gas fields. Then, of course, there's the transport issue. It's been discussed quite a bit. We're looking at both pipeline, which is common today, and ships, which is evolving. The long ship project described by Amy is an excellent. Of course, we're using that as a go-by very much so. And we're just studying how these technologies can help CCS and ASEAN. And the third is policy. We would like to understand the current policy that may be applicable for CCS. And we want to study how ASEAN countries could establish policies and regulatory framework to allow CO2 to be sequestered in an economical manner. I think I've heard repeatedly today, there's no physical or chemical reason why we can't do CCS today. Policy is critical path. So what are the preliminary results of this study? Our initial assessment focused on, as I said, depleted oil and gas fields. This includes EOR, which is a smaller subset. The aggregated numbers are displayed here in bubbles. And for example, Indonesia had about 18 gigatons of CO2 storage capacity and Brunei is about 7. The storage capacity of all these countries together, just the depleted oil and gas field, is about 60 gigatons. So it's within the range that you saw earlier today. And I agree with Prof. Lau and others that we're talking about at least 100, if not several hundred years of CO2 storage, because it's likely that we'll probably only sequester maybe 5 to 20% of this total CO2 that needs to be mitigated. The rest needs to be handled by growth of renewables as fast as you can, the ASEAN power grid, and all these other things. Everything needs to be working at once. So I'm just talking about the sequestration aspect. The key message is that there's plenty of sequestration capacity. Just looking at the depleted oil and gas fields, aquifers are expected to yield multiple times the numbers that are here. So we're really confident that all of the countries in Southeast Asia, all 10 countries, will have enough capacity to sequester their needs. So what about transport in this? If the distances are short, you can use pipeline. For example, as shown here in red, you've got Malaysia and Indonesia, where in some cases, maybe we can repurpose existing pipelines used to import natural gas to Singapore, repurpose them to export CO2. Obviously, there are issues associated. It's not the same gas and so on, when we're looking at that. For longer distance shipping options depicted in blue may be used here. So for example, Singapore to Brunei, Singapore to now, the recent IEA GHG report outlined underlying technologies for transporting CO2 via pipelines and ships. And this top chart shows kind of the phase diagram. And the idea is that in pipelines, you probably want to pressurize up to somewhat above the pressure needed to actually inject it into the subsurface. That way, as the supercritical CO2 flows through the pipeline, and it'll lose some pressure, right, because you've got some friction, some energy loss. But by the time it gets to the reservoir where it will be sequestered, it has enough pressure to be injected subsurface. On the other hand, ships, you don't actually want to, it's problematic to pressurize at that high, but you can have lower temperatures, so you can have liquid CO2 for ships. And then if you just compare distances with costs and so on, you can find a crossover point. For the case presented here, transportation of about 2 million tons per annum, You can find a crossover distance of about 500 kilometers. That really can change depending on the assumptions in your model. Okay.
Adam, so, 3 more minutes left.
Yeah. So finally, let's put it all together into a conceptual roadmap for Singapore, indicating kind of a potential development pipeline. And in particular, I want to emphasize we probably need to do multiple things at once, so that we can actually solve the problem when it still matters. First of all, high concentration CO2 sources, such as from partial oxidation units or hydrogen production, can be addressed with commercially available physical sorbents. And that's commercial. It's not that expensive. Singapore has that. We can do that for certain sources. For lower concentration sources, you can do commercially today liquid amines or aqueous amines. Meanwhile, we're working on R&D, as I mentioned earlier, to sort of lower the cost, lower the complexity, lower the physical footprint. And this is a notional, conceptual kind of where they are in the pipeline. We think carbonate fuel cell is next, but a lot of the other things we're working, could come next. And then finally, on the disposition side, geosequestration is probably the thing if you do it nearby next. Meanwhile, progress the ship option, stealing as much as the ideas from the Longship Northern Lights folks as we can, and while honoring IP. I don't mean really stealing. I just mean good ideas. And then we believe in some of the R&D projects, but they're a bit longer term. And this came up earlier about utilization. Utilization. I think this is consistent with what I heard Amy and others say. It's important to do, probably significantly smaller volumes, since the products you would make don't necessarily need such large volumes. It's also further down the pipeline, so work it, but don't count on that to solve Singapore's problems in the next 20 to 30 years. So, summary: CO2 capture and sequestration we think is an important part of for the world, and we think it's probably part of Southeast Asia's solution to decarbonize. ASEAN region has sufficient capacity, and we think Singapore can play a very active role. One last thing as an example, because we're talking about ways to offset the cost, right? Because that's why people are thinking about EOR. Conceptually, Malaysia has announced plans they want to do a CCS project. Indonesia's announced plans that they want to do CCS. In both cases, they're talking about CCS from CO2 from natural gas fields that they want to produce. So yes, that's important, otherwise it would be vented, but that's not really anthropogenic. On the other hand, they'll need help, financial help, perhaps in an imagine chain where we've got CO2 to sequester its CO2 in some of the same fields, provided there's enough capacity, and we think there is, that can help offset the cost for Indonesia and Malaysia. So it's another mechanism by which we could actually, incentivize. And there are all these discussions about hub models and so on. So those are all really exciting for the future of Southeast Asia. Thank you.
Thank you, Adam. Thank you for the very interesting presentation. So I would like to call next Dr. Richard Heyn from the Sintef Industry Process Technology, Norway, who's going to talk about the carbon cycle options for CO2 utilization. So Richard, floor is yours.
Thank you. I need to get squared away here. Do you see my, is my screen?
No, we don't.
Okay. Now I've.
Yeah.
I don't understand why it's not showing up on my, there it is. Sorry. And let me make it full screen here. Okay. I think everything is squared away now.
Yeah, good. Thank you.
Yeah, thank you for the invitation. This has been interesting. I'm a simple chemist, and so my focus here is going to be on chemistry. And what I would like to do is talk about CCU. From a philosophical point of view, I'll try to explain to you what it is and what it isn't, what its limitations are, what its advantages are, why it could be useful, and why it's not a panacea. And I am in agreement with Adam and some of the other commentators and speakers here, is that we need all the tools in the toolbox. We cannot exclude anything from the search for a solution to climate change. So I'm not an anti-CCS guy at all, because I understand we need the technologies simply based on the amount of CO2 that's emitted. So don't get me wrong by some of my comments, but again, we need all the tools in the toolbox. And I just want to make an observation that I'm the third expat American speaking here in a Norway Singapore Science Week. I'm sure it's a small sample size, but I'm not quite sure what that really means. Anyway, before I get started, I'd like to introduce a little terminology. I'm going to be using the term CCU for the carbon capture and utilization. This has been used in other terms. I think the most popular term these days is CCUS, which is fine. I know some people like to use the term carbon reuse, which I think is a daft description, because if you emit CO2 from burning a fossil fuel, it hasn't really been used, so how can you reuse it? I will be introducing a term called defossilization, which is related to the term of decarbonization, but is a little different. And then also talk about something called carbon avoided, which is reducing the CO2 emissions by changing the carbon source. So the title of my talk is the carbon cycle, so I thought it was appropriate to actually show the carbon cycle. And this is an example I've taken from Britannica, and I think every single picture on the web looks something very, very similar to this. And one of the things that I find very, very striking about this slide is that everything on here are all natural processes except for this. And I've seen people argue that, well, you can't stop combusting fossil fuels, because then you'll disrupt the carbon cycle, which is completely wrong. The carbon cycle existed long before we were here and started burning fossil fuels, and the carbon cycle will continue to exist long after we're gone and stop burning fossil fuels. So it's this aspect which people consider to be part of the carbon cycle, which is really not, and is the source of our issues. And consider CO2 as a waste from a combustion process, and you look at waste management, you have this hierarchy here, and what you end up is, if you really want to prevent the waste, then you have to do renewable energies. If you want to minimize the waste, you have to reduce the use of fossil fuels. And if you really want to dispose it, then you do CCS. And this is not to denigrate CCS at all. It's just simply to say what CCS really is, and that is a waste mitigation technology. And so if you really want to solve the problem and not the symptoms, in the long term, what we have to do is we have to decouple our dependency from fossil fuels from our way of life. And a corollary to this is that the people talk about long-term storage of carbon. For example, Amy mentioned how the climate program in Norway only funds the long-term storage of carbon. The longest form of carbon storage is leaving the coal, oil, gas already in the ground. And so then we don't need to, why spend all this focus on CCS if the best way to do it is just to leave the carbon where it is? Now, I understand there are issues with this, and we don't want to go back to the Stone Age. So we have to continue looking for solutions that maintain our standard of living while at the same time addressing climate change. But a lot of the focus around climate change is the energy challenge. And what I would like to talk a little bit about is the materials challenge. And the materials challenge is around us is made of carbon. We're carbon-based life forms. We live on a carbon-based planet. Everything that we touch, everything that we use is either made from carbon or made with carbon and energy. And so the primary source of that carbon and energy are fossil fuels. And if we were to, say, decarbonize the energy sector and renewables, where is the carbon going to come from for all the stuff that we need? And this is what CCUS actually ends up being, is because you can decarbonize the energy sector, but you cannot decarbonize chemicals and materials because carbon is an integral part of all of that. So you have to defossilize the production of chemicals and materials. How you do that is that you use the carbon that we already have around us. And by this, I mean the biosphere, the atmosphere, and the hydrosphere, and not the lithosphere or the the geosphere. And I like to use the term biosphere because I think that that is a lot more easier to visualize in any case. And those carbon sources then are CO2, which is then becomes CCU, biomass, which essentially is just CCU that has already gone through the factory of a green plant, and already processed carbon materials that are already in the environment, for example, plastics. And then so what CCU does is it reduces the emissions, CO2 and climate change emissions, by reducing our fossil fuel dependencies. And this is the whole concept of carbon avoided. And this is why and the reason we need all three of these options is simply because if there's too much CO2 to be emitted to be converted into chemical products. And so what I've done here is a very simple magical experiment where I've taken every single carbon atom in a CO2 molecule and magically put it into a different molecule. And I haven't considered how you do that and what the CO2 footprint of that process may be or anything else. And so methanol, which is probably the largest bulk chemical in the world, is produced around 110 million tons per year. If every single carbon atom in all the methanol that's produced was made from CO2, you would need around 150 million tons of CO2 per year. If you did that with gasoline, you would need 2.5 gigatons of CO2 per year. And in 2019, global energy-related CO2 emissions were 33 gigatons per year. There is no way that you're going to be able to convert all the CO2 that is emitted into chemicals or materials. The second option is that there's not enough biomass to provide food and also carbon for all the stuff that we need. So this is why you need both. And actually you need the third bit as well, because we would like to get rid of CO2 emission. We don't have enough biomass, so then you already have to use a carbon that is in the that we've already used, the plastics and all the other carbon-based materials that we've already made, and recycle that carbon. So CO2 is great for making simple and small molecules because you have to, and I'll get to this in a minute, but you have to reduce it, and so you're actually relatively limited in what you can do with it. Biomass is great because it's already functionalized, so you can break it up in theory to larger, more functionalized molecules, and then these plastics, these carbon materials can be gasified into, for example, synthesis gas. And that is one of the things that, for example, the EU will be looking for projects for in the coming framework program, is the idea of using plastics as a new type of refinery. So here are some CCU facts that need to be repeated, and my apologies if everyone this, but I feel that if there's simply one person in the audience who has a little aha moment, it's worth spending some time on it. CO2 is in a thermodynamic well, and so you need energy for its transformation. And so, for example, if you have a fuel and you burn it, you get down into this thermodynamic well here, you get the energy out. And if you want to make fuels again from the CO2, you have to put the same amount of energy back into the CO2 molecule at a minimum to make the fuels again. Now, I say at a minimum because there's going to be a process involved in that, and that process will also involve energy. So the energy has to be resourced from renewables. And the new process, any new process that you make from CO2 has to have a lower emissions in the state-of-the-art process. Otherwise, there is no point. So, and I have an example here that I'll show you. And this is why you need have to do a proper LCA with the same boundary conditions in order to assess your technologies. So, for example, taking the methanol example, the state-of-the-art methanol synthesis is from syngas, which is a combination of CO2 and hydrogen. And the CO2 emissions for that is about half a ton of CO2 per ton of methanol. If you then say, great, I'm going to use CO2 and hydrogen to make my methanol because CO2, I'm using the CO2 and it'll be a greener process, then the question becomes where you get that hydrogen. And if you use, and the standard technology for making hydrogen is the steam reforming of methane, which is a very carbon intensive process. So if you make methanol from CO2 and hydrogen from steam reforming, your CO2 emissions actually go up. But however, if you then take CO2 and hydrogen from water electrolysis, which you're then doing with renewable energy, you have overall negative CO2 emissions. And what's not important is not only that you're using up your CO2 because the CO2 is going to the methanol, but the difference here between the state of the art and your new process, which is over a ton of CO2 per ton methanol. So one of the issues with CCU technologies, and this has been pointed out before, is that there are actually relatively few CCU technologies which are technologically mature enough to be used. And to me, this is one of the biggest issues with CCU is people would like to do something with the carbon dioxide. They understand the fact that if you do CCU, you're making something that has a monetary profit. And then people get stuck because there simply aren't that many modern or mature technologies that you can use for the CO2. And I've listed a few here. One of these things, for example, if you're going back to the fuels, methanol is at a Tier 9. There's a company in Iceland called Carbon Recycling International, which is using energy from geothermal to make carbon negatives methanol. They're looking now at other places in the world where they can use renewable energies to do the same sort of technology. Formic acid doesn't quite have the market of methanol, so that's a bit of an issue. I personally have never understood why somebody would like to reduce CO2 to methane, but that's around a TRL6. And if you have methanol formic acid, then you can start getting into some other sets of molecules up here. Urea is made from CO2 today on the scale of about 175 million tons per year. You can make salicylic this acid here, which is part of aspirin. This is a relatively lower market value. These carbonates are really interesting molecules, in my opinion, and they're made today kilotons per year. And Covestro has recently started making these oligomers that they're putting into their polyurethane formulations for their mattresses, which is, again, very small. But this is a very, very limited set of high TRL technologies that you can do with CCU.
Richard, 3 minutes left.
Okay, thank you. So how do you advance the state of the art is that you have to look at high energy reactants, and you have to look at reactants that are sourced from petrochemical sources that do, and a lot of these reactants are from petrochemical sources that have a large CO2 footprint. So if you really want to use CCU as an agent of change, you have to look at CO2 conversion technologies that use reagents that are preferably sustainable and non-petrochemical. So for example, one of the issues with CO2 is that since in a thermodynamic well, you have lots of chemistries that are limited by thermodynamic yields. So it would be really great, for example, if you could make these cyclic carbonates I mentioned from CO2 and the biomass. But this is a very low equilibrium yield. And as a comparison, you can make the same molecules from CO2 and a high energy molecule like an epoxide, but the problem with this is the ethylene oxide here has a very large CO2 footprint. So you really need to start looking at ways to couple your catalyst development and your process development to develop CCU technologies. And another option is to start looking at coupling reactions together so that to improve product yields. And this is the idea of using Le Chatelier's principle to our advantage. And this is an example that we have in an EU project where we're looking at the equilibrium limited reaction of CO2 and hydrogen to methanol, but in the same reactor and with the combined catalyst, taking that methanol to propane and propane, thereby improving the overall CO2 conversion to more useful products. Oh, CCU advantages, limitations, and needs. The solution to climate change is decoupling our society from fossil fuels. And this is much easier said than done because we want to maintain our standard of living. Economies are growing. We want to take people out of poverty. All of that requires energy. And I understand all this, but we have to look at ways to go cold turkey, if you will, and reduce our dependencies on fossil fuels. Energy can be decarbonized, but chemicals must be defossilized. That means you have to start looking for ways to not use fossil fuels to make chemicals and materials. And that is what CCU is all about. It's an important aspect for the defossilization of chemicals and materials by using alternative carbon sources than fossil fuels. The problem, of course, is that the number of high TRL reactions is relatively limited, and so you have to start doing fundamental research now, looking for collaborative breakthroughs in catalyst and process development, using new reagents and a minimum of renewable energies, because I'm sure that there are perhaps better ways to use hydrogen than necessarily reducing CO2 to chemicals and fuels. So I think I'll close there. So thank you very much for the invitation and for listening.
Thank you, Richard, for the very good presentation. So we have, yeah, we could like to open the floor for some Q&A. Anybody?
I guess to Richard, I appreciate your main thesis, but you know, the reason why fossil fuels persist is because it's extremely inexpensive, it's extremely efficient way for the world to use energy. So I mean, that's the main reason, right? And right.
Yeah, I understand that it's fossil fuel. The energy density of fossil fuels is hard to beat. So I understand.
It's hard to beat. Mother Nature did to make it, you know, over millions of years. Absolutely. Yes.
Any more comment from the floor? Actually, I think there was a comment about how is the overall. This I think came from A-Star. I mean, was it to Adam on how is the overall carbon footprint for CCS is taking into account the emissions for transportation to other countries. I know Adam, you responded over the chat. Maybe you want to share a bit more on that.
Sure. I mean, actually, you know, I responded two ways. One is that, you know, the literature and others have talked. It's a valid question. Unless you think about it, it's not obvious. Does it make sense? But it does. It turns out the emissions associated with the compression and transport of CO2, even long distances, can be rather small component of the total volume of CO2 sequestered. So it makes sense from an LCA. But I also said in my response that if we end up, you know, thinking about specific ASEAN-based CCS project, a detailed LCA should be done. Absolutely. So.
Thank you. Any more? So actually, Adam, I mean, one more question that I have. I mean, from the ExxonMobil standpoint, you gave us a little bit of an overview, you know, on which are some of the initiatives around CC carbon capture. I mean, but can you share maybe a bit more on maybe what you see actually? I mean, out of the many initiatives, which one maybe are most promising and they might have a better impact or faster impact than others?
What I mean, of like everything people are thinking about for energy?
No, from ExxonMobil standpoint, based on your presentation.
So I focus the presentation on CCUS, but obviously people are, first of all, wind and solar is just growing like crazy. But to Matteo's point, not fast enough. Not fast enough. I mean, you know, if you know, people are saying, why can't you just decarbonize by just growing renewables? And it just can't grow fast enough, and it, you know, at a reasonable cost for much of the world. We are currently, our big thrusts are CCUS, biofuels, and process intensification, meaning reducing the emissions associated with our own, you know, commercial operations. Our research lab, corporate research lab out of New Jersey, does you know everything from renewables and so on. But you know, from things that we're trying to scale up right now, it's the three that I just mentioned. And you know, because CCS is tied to blue hydrogen, right? Because hydrogen it wasn't a topic this time, although it was a topic of the Norway, Singapore webinar last spring. You know, they're tied together quite a bit. And once again, the argument is, why would you make blue hydrogen if you can make green hydrogen? And the issue is scale, speed, cost for now, you know. And so, you know, if hydrogen becomes an important part of a decarbonized, or as Amy pointed out, a de-CO2ized future, then blue hydrogen is going to be pretty significant, and it's another area of interest in this region.
Let me comment here to give an example. There has been a study in Germany to replace coal-fired and fossil fuel fire power plants by renewable energy. At the rate at which they're adding renewable energy in Germany, it would take 20 years just to do that. 20 years just to decarbonize the power industry. Now, should we wait for 20 years before we decarbonize other industries? Answer is no. So there's an urgency there to meet the climate change, right? Now, power industry is the easiest industry to decarbonize because you can just use solar, wind, and hydro. But if you look at the transport industry and the industry, those are much harder to decarbonize. And therefore, there's not enough green energy to decarbonize the major sectors, the industry sector and transport sector. Therefore, you need CCS or you need the blue solution before you can get a green solution. Yeah.
Thank you, Prof. Lau. Richard, do you want to say something?
Yeah, just a few comments. First, with regard to atom and blue hydrogen, my thinking on this has evolved, and I would even maintain that you can use gray hydrogen if it helps you accelerate hydrogenation technologies. Because we simply can't sit around and wait for green hydrogen and then say, okay, now we have all this green hydrogen, let's find the best way to use it. So I fully support your comment that we need the blue hydrogen. With regard to Professor Lau's comment, my question then is, if you compare transportation and the traditional power sector and other process industries, what is the greatest CO2 emitter? And I would argue that it's the power sector. And if Germany can decarbonize the power sector within 20 years, I think that's great, and they shouldn't stop.
Well, they're not stopping actually. But the question is, do we have excess renewable energy to decarbonize the other sectors? The answer is no. Because the most efficient use of renewable energy in terms of CO2 emission is to decarbonize the power sector.
See, one of the big issues here, I think, is that if no one knows the answer to the question, what is the best use of 1 kilowatt hour of renewable energy? And there is no one simple answer. And so it depends on where you are and where the energy comes from and all sorts of things. So it's until you have a good idea of the best use of what renewable energy is, you have to follow all the paths.
Yeah, no, I think we have an answer to that. If you look at the amount of CO2 generated by fossil fuel used to generate electricity, either by natural gas or coal, you know how much CO2 is generated per kilowatt hour. And if you use renewable to replace fossil fuel, that would be the most efficient use of fossil fuel, of renewable. Now, if you turn renewable into hydrogen, green hydrogen, and use it to replace fossil fuel in terms of as a heat content to generate heat for industry, that would be a much less efficient use of renewable energy. So the most efficient use of renewable energy is to decarbonize the power sector by replacing fossil fuel. That's known.
Okay, great.
And that's been
and then my argument or my rebuttal is then you're addressing the biggest emitter.
Right.
So
we don't have enough renewable point to
then we're in agreement.
Power sector.
But Professor Chung, just the precision on, or just a point on the 20 years time frame. The 20-year time frame is with the current framework. Yes.
Right.
And you know that Europe is trying to get up its economy in one other way, and the Green New Deal has come to probably help in that impossible task. And they want, and if they finally wake up from their sleepiness, they will change the way Europe is getting its electricity from, because the resources, renewable resources, are there. It's just a matter of putting the energy, not the renewable energy, the financial and the brain energy, in that direction consistently. Because my fear of the carbon capturing on the power sector is that you in a way prolong the life. So, you know, if I have a power station that produces 1 gigawatt, I put carbon capture and sequestration, and I decrease the efficiency of 15%. Then I need more fuel in order to provide the same amount of electricity. So that is actually not solving the problem at all. But in a way, Adam is also right that at the current stage, it's not fast enough. But this is a point. It's not fast enough because we are not fast in terms that we don't have the material to create that. We are not fast enough because there is no the will to do that. And I feel, as far as I see around, in terms of economical payback, everybody wants to get into solar, wind, or whatever, because it's getting. So that's not any longer a limiting factor. Anyway, stop here.
But you have to look at outside Europe. Yes, in Europe, you can decarbonize maybe faster. By actually, the cost of new power plant by renewable is almost at parity to fossil fuel. So if you were to build a new power plant, I would use renewable. But if you look outside Europe, okay, if you look at Southeast Asia, where we are in, we are not even beginning to decarbonize the power industry, let alone transport and industry. So if you look at the world as a whole, there's a lack of renewable there's not a lack of renewable energies. And therefore, before there is enough renewable outside Europe, we need to reduce the carbon content in the air. And CCS is the only game in town, basically, in terms of removal gigatons of CO2 that we produce from all the industries.
So loud. I apologize because Alessandro is gonna shoot me. But this is exactly the core. You remember that in the question I said, what is the difference between Singapore within the value chain of the oil sector and Norway within its value chain and its position in Europe and position in Southeast Asia? And actually, you are start to getting to that part of the argument that things are different. In my opinion, the way Norway is going in Norway is a bit anachronistic in a European context. So they should do that. It's not bad to do that, but do that elsewhere. Anyway, I stop here.
Yeah, thanks, Matteo. Yeah. I mean, yes, sorry, I need to interrupt this very interesting discussion, but we are running a bit behind in schedule. So I would like to move on with the presentation. Then probably we can reinitiate this discussion if we have some time left towards the end. So I would like to invite Dr. Hans Bernstein from the Arctic University of Norway, who will be talking about his presentation title is Leveraging Microbial Ecosystems for Innovating CCSU Technologies. So Hans, floor is yours.
Great. Thank you. Good morning. Good afternoon. I assume everybody can hear me.
Yes.
And you can see my screen. Thumbs up for seeing my screen. Great. So we'll move on. My name's Hans Bernstein. I am a plain flavor chemical engineering by training, and I cut my teeth in the U.S. Department of Energy system at the Pacific Northwest National Labs, mostly on bioenergy and genome sciences program. I have an error message saying that the network is causing poor call quality. Can you still hear me and see me?
Pretty well, yes.
Okay.
Maybe you want to put your presentation slides in, so the slides in presentation mode, maybe? So we can see the full screen?
Absolutely. Anyway, I am now at, can you see the full screen in presentation mode now?
Not. Actually, I don't know if you are having...
There we go.
Yeah, okay, please.
Yes, perfect, yes. Okay, so I'm now in Northern Norway. I moved here because I was attracted by the mission of the Arctic Center for Sustainable Energy, which is a multidisciplinary institute that addresses multiple sustainable development goals, including management of greenhouse gases, where I play. I also run a research group that we've kind of refounded called the Microalgae and Microbiomes Research Group, or the M2RG, where we have 3 focus areas: microalgal biotechnology for CCSU, marine microbiomes, so sort of a fundamental ecology perspective, as well as synthetic biology, specifically of marine microorganisms. So today I'm going to kind of talk to you about this. and specifically how we leverage microbial ecosystems or biotechnology for CCSU. Okay, so the advantage to going late in a session like this is that we get to know our audience, and I really appreciate some of the earlier perspectives that we need to bring all of our solutions to the table. We have a major challenge ahead of us, perhaps the greatest challenge that humanity has had to face, and there's not a single silver bullet or a single solution that will get us out of this. My argument is that there will be different markets and that biotechnology has a role to play in this. It's certainly not going to be the largest role. It's in the short term, it's not going to compete with geologic sequestration or the combination of green hydrogen, CCU to methanol. But there's the rate of change for our understanding of biology and biotechnology is so rapid with the genomic era and the synthetic biology area that there's a tremendous amount of innovation, especially in the short term, where we have small and medium scale industry looking more at how they can create a value chain and still try to be environmentally sustainable, where they can't really pay the penalty for a carbon tax or large-scale sequestration. So I'm going to give you a couple of examples just to kind of drive this point home. Two themes I want to hit first is I'm learning the art of the webinar, and I'm learning that going into lots of technical detail is not always necessary and does not always capture everybody's attention. But as a scientist and an engineer, I love to grind out the details so we can have that conversation afterwards or offline. And the other point I want to make is that biotechnology for carbon capture, utilization, and sequestration is no longer at the bench stage where we're simply running experiments in an incubator and writing perspective articles and saying what could and should be done. We're actually at the point where we're in pilot scale or pre-industrial scale. So this first example I want to show is local. It's from northern Norway. We call it the Finnfjord project. So this is a collaboration between the Arctic University of Norway and the company Finnfjord AS, which is a metallurgical plant. They've produced ferrosilicon, which they produce by cooking together iron, quartz, and various carbon sources from wood chips and coal to produce this metal, which is used in the steel process. It's very energy intensive. They are the largest emitters of carbon dioxide in the region, and they have a very good outlook on the fact that they need to become more sustainable. So they've set their own goal of reducing their emissions by 50% in the next 10 years. And one of the technologies they brought into this portfolio is algal carbon capture and utilization. So they teamed up with UIT, and we implemented photobioreactors. One of the advantages of this plant is they have a lot of excess energy and they're directly located on the seashore. So we have seawater and energy to work with, which can allow us to power LED lights and also pump in very large volumes of seawater and return it back to the ocean. So we're able to grow endemic or natural algae that were sourced directly from the ecosystem adjacent to the plant. And we've chosen them based on their nutritional quality. So we're able to convert a portion of the carbon dioxide from the flue gas, or as much as we can get dissolved, or as much as we can pass through the mass transfer limitations into biomass. And then this biomass in itself is the value chain. And we've chosen it in a way that it can support the local aquaculture industry. So there's been a lot of talk about CO2 and a little bit of talk about methane. But as all of you know, methane is also a major greenhouse gas. It has roughly 8 times the heat trap effect of CO2. And it's also a wonderful resource for biotechnology. So you know that it's produced by human industrial activity. It's also produced naturally. So I'm showing here just an example of one figure I'm showing is the Ekofisk oil platform, which has historical relevance for Norway. I grew up in the Rocky Mountains of the US, where small-scale oil and gas extraction is part of the daily life and part of the daily landscape. And these flares or these torches that we see are really common. So as you know, when we often extract natural, sometimes it's either not a continuous enough process or there's not enough infrastructure to use that natural gas as a product itself, in which case it's flared and burnt into CO2 and emitted into the atmosphere, or in some small scale cases, it's just directly vented into the atmosphere. Another major emission point is the digestion or decomposition of organic waste. So I'm showing you a picture of a landfill located near the coast in northern Norway. And microbes facilitate the breakdown of organic material, specifically methanogens, and this represents a large emission of methane. Some people have tapped into this to capture what we call landfill methane or biogas for compressed or liquefied fuel sources, and we can also encase this and use the pressure to drive turbines. But the reality is the majority of human-produced organic waste is simply decomposed and emitted back into the atmosphere as a greenhouse gas. So we have technology to remediate this as well. This is a project that's very near and dear to my heart. I've been working on it for many years, and where we have constructed a simple microbial community based on two organisms, a methane oxidizer, which is able to take the methane and turn it into biomass, and CO2 is a byproduct. We couple that with a photosynthetic microbe, either a cyanobacteria or diatom, which can take up the CO2 produced from the methane oxidation process, as well as the CO2 in the stream. If we power this with sunlight or LEDs, the byproduct of photosynthesis is oxygen, which is required by the methane oxidation. So we have designed this sort of metabolic exchange where we can take advantage of division of labor of two different microorganisms, produce more biomass, and it's quite flexible. So we can use different feedstocks such as natural gas, raw biogas, and landfill gas. The major development we've made recently is to exchange the different types of microorganisms. So we can think about this as a flexible platform that we can have different players on the team. In this case, we're trying to get it to work with marine microorganisms such that we can supply this nutritional consideration that could help support a value chain in the aquaculture industry. So the idea is that we have a gas stream either from natural gas or anaerobic digestion. We send that through a closed photobioreactor. We convert as much of it as we can into biomass. There's mass transfer limitations and solubility issues, especially with methane. And then the remainder of it can either be upgraded to biomethane or combusted for heat and electricity to power either this process or other adjacent industrial activities. So those are just two examples to kind of drive home the point that biotechnology does have a role to play, especially in the CCSU framework. But there's so much more that can be done. So where will we look? Where will engineers look for new inspiration or new motivation for biotech? I really love using this image in my presentations. The landmass you're looking at is northern Norway. It's actually just north of where we are now. And this fractal plume-like shape you see is the spring algae bloom. So these are diatoms blooming in the Barents Sea, and this represents a major carbon drawdown event annually. It also supports the entire ecosystem, which in turn supports two major international fisheries, both that of Norway and Russia in the Barents Sea. So as an engineer, I've always been interested in where mass balances and life cycle analysis. And as we start looking at the carbon cycle, the globe and carbon cycle, it strikes me that microorganisms are related to, and in some cases, even the major controllers of most of the large carbon sinks on the planet. In fact, the only one at least on this diagram, that is not directly related to microorganisms is industrial emissions. But that's perhaps where biotechnology comes into play to help with point source remediation. So for the rest of this talk, I just kind of want to, I guess, change gears from what we have been talking about and try to look to nature to drive new innovations. So I'm going to focus on three of these biomes: the ocean, the deep subsurface, and the terrestrial or soil system. So the first one I want to point out is the marine biological carbon pump, and this was brought up a couple times in some earlier presentations. But this is a major sink of atmospheric carbon dioxide that occurs naturally, and this is one of nature's ways of protecting against the current emissions. So CO2 is drawn down by microorganisms in the ocean, specifically photosynthetic microorganisms. It's converted into biomass, but it's also converted into small or dissolved organic material that we call DOM, it's that DOM is usually rapidly consumed by heterotrophic microbes. So these are the microbes that sort of feed off of the algae and immediately remineralize the CO2 and push back into the atmosphere. However, a significant portion of it remains as what we call refractory dissolved organic matter. So this is the organic matter that is resistant to microbial degradation, and it persists in the ocean for thousands of years. So this is long-term carbon storage. Also, microbes coaggregate together. They either adsorb to other surfaces or are transported deep into the subsurface at a significant rate, which can result in long-term geologic era storage. The pool of dissolved organic carbon is roughly the same amount as the current atmospheric carbon dioxide that we hold today.
Hans,
Yeah,
three more minutes to go. 3 more minutes to go. Thank you.
Okay, so this represents an opportunity for new CCSU biotech, and I do mean coupling carbon utilization with carbon sequestration, where many of us are interested in taking advantage of the ability of microbes to make this dissolved organic carbon, as well as harvesting the biomass as a value chain. The next major carbon pool is the plant soil carbon pump. And so this is a concept where plants draw CO2 from the atmosphere, as you know, and of course pump it down into the ocean, where it's either consumed and remineralized to CO2 by microbes or locked away in long-term carbon storage. So this is perhaps the largest natural carbon pool that we have, but it's also subject to high levels of uncertainty due to global warming and changes of how we're using our lands. So this represents another new concept, or CCSU concept, where we're working with a group in California for genetically engineered crops that either make deeper roots, so the roots penetrate the earth deeper and resist decomposition, and or make compounds that are resistant to microbial degradation, such as this compound suberin, which is the main compound of cork. So the plants can be harvested as they would for either bioenergy crops or food crops, but are locking more carbon away into the soil as soil organic matter, which is essentially recalcitrant. And the third concept, I think, goes with the deep subsurface, which is an ecosystem that we currently don't have a lot of information on, but it's also the place where we plan on storing much of our future carbon, CO2. And we've heard a lot about that, so I'm not going to go into it in detail. But they were working with other groups in the US to build a biotechnology that helps us lock away the carbon by taking advantage of the ability of microbes to produce biofilms. So biofilm was when a microbe attaches to a surface and also produces what we call an extracellular polymeric substance. And they can also change local pH to create biomineralization or the precipitation of carbon minerals, and this concept of biocement. So if we can, as we push carbon dioxide into deep subsurface and we stimulate microbial growth there, we can use this to seal geologic formations. And there's also an unknown there of how the ecosystem will respond to that and perhaps activate CO2 uptake or conversion of CO2 to biomass inside of the deep subsurface. So that's just a short overview. I want to kind of leave it with what is the link between microbial ecosystems and biotechnologies, and that is that microbes have a large and undiscovered potential that can drive new innovation for many technologies, but specifically for CCSU. And with that, I'd like to just thank the UIT and the Arctic Center for Sustainable Energy and open it up for questions.
Okay, thank you, Hans, for the very interesting presentation. So let's move into the next one, the last but not least, given by Professor Praveen Linga from the National University of Singapore. And the title of his presentation is Carbon Capture and Storage via Clatrate Hydrates, Prospects and Challenges. So Prof. Linga, the floor is yours.
Alessandro, can you hear me? And
I can see the slides and you. Yeah, all good.
Okay, how are you doing with time? I am sure we are offshoot by quite a bit. Let me try to make it short. The advantage of putting me in the last is a number of speakers have already spoken about CCS. so I don't need to spend time on introduction. So today I'm going to talk about the carbon dioxide capture part. Most of the speakers generally presented the overview of CCU and CCS, and also Hans gave an excellent talk on what we could do on the utilization side, but not on the chemicals, rather on the microbial aspects of it. So I'm Vice Dean and Dean's Chair Associate Professor at NUS Singapore. I joined NUS 10 years ago after finishing my PhD from UBC. I mainly work on gas hydrates. In fact, my entire career of 16 years, I've been working on gas hydrates, looking at both fundamental and applied aspects of technology development. Mainly, I work on environmental sustainability options related to carbon dioxide capture and storage, seawater desalination. I'm also interested in gas storage, energy recovery, and I spoke last week about some of our work on LNG, cold energy utilization. So again, this is a one-liner. CO2 is the major contributor to climate change. Adam earlier presented ExxonMobil's report on the scenarios. So essentially, all of these show that CCS is a critical technology component that is going to enable this transition, while we hope that renewables and mainly triggered by wind and solar is going to actually speed up and come to the situation where we can start to decarbonize or de-CO2 emissionize our world. So if you look at role of CCS, this slide, I'm a chemical engineer, so I like looking at numbers. If you look at the sector that is going to have the highest influence or the largest impact, it is actually the power sector. We had a few speakers also discussing about this aspect. So it is possible that CCS can contribute nearly 17% into the power sector aspects of it, while it can also play an influence in the industry sector. This is mainly where petrochemical industry already has streams which are in the range of high CO2 concentration, right? And so kind of, I want to drive home that CCS is a very critical component in terms of looking at global warming mitigation strategies. Now, if you look at how CCS works, or CCSU, if other speakers may like, you need to capture CO2. Where is that CO2 coming from? CO2 is mainly driven by the power sector, and the second major sector is transportation. Transportation sector does not give us the advantage of a large-scale point source capture. Rather, power sector gives us that. If you look at the power sector, there are three different ways how you can generate electricity. We call them post-combustion, pre-combustion, oxy-fuel combustion approaches for CO2 capture. In a post-combustion capture, what we are looking at is the conventional way of producing electricity, which is done all over the world. Basically, you combust coal or any other fossil fuel with air, and you end up with a CO2 stream in the exhaust, which is typically 5 to 15%, right? So in a CCSU strategy, you want to actually partition this CO2, make it into a pure CO2 stream by applying any technology that is mature, and you want to then utilize the CO2, or you want to dispose it off into the storage sites. The second option is pre-combustion capture. Pre-combustion capture is where you actually take your fuel, put it into a gasifier, and then by coupling it with a water gas shift reactor, you would end up with a stream that has a binary mixture of CO2 and hydrogen. The CO2 composition in this stream is typically 20 to 40%. I must say the number is closer towards 40% when you go through this route. In this route here now, before you produce electricity, you are actually stripping off the CO2 or capturing off the CO2. Right? If you do that, that becomes pre-combustion approach. So essentially in this stream, you're separating a CO2, which is close to 40%, from a hydrogen stream. That's what a pre-combustion capture means. And then the downstream part all applies the same, what you do with the CO2. The third approach is oxy-fuel combustion. Oxy-fuel combustion is a process where you actually separate nitrogen out of the air. So basically that means you would end up with a relatively pure CO2 stream as an exhaust gas. And that CO2 can go further for upgrading and then for sequestration. These are the three main approaches related to power sector. Now, if you look at Singapore scenario, the power sector is is mainly dependent on this route, but we don't use coal, we use natural gas as a feedstock. So 95% of the electricity that we generate in Singapore is from natural gas. So that's why 2 years ago, I wrote an opinion article in Straits Times saying that Singapore is almost on the cleaner slate if you look at the fossil fuel contributions and the CO2 emissions with respect to the fossil fuels that we are using, because all our energy is coming from natural gas. Solar is the only other option that can come in the renewable scale. We are very bad at wind. Solar is also not a great prospect. Despite all the effort that's gone in, we are still around 2% as solar contributing to the power sector in terms of energy generation. However, we have a very major presence in the petrochemical industry. That is where CO2 stream is also possible. Perhaps Adam touched a little bit on that. So it is possible to also capture CO2 from the industrial processes. It has been going on for many decades. The technology is matured if you look at this route of concentrating CO2. Now, if you look at the prospects for new materials, Adam touched it in a different scale. I want to come back to this slide where I want to focus that this is where gas hydrates as a technology for carbon dioxide capture stands at. It requires efforts. So I would say the TRL level is at this point is less than 2.5. So we have to continue to take it. So the time to commercialization is quite far if you're looking at this part of the graph. Whereas this is where your traditional solvent amine-based chemical and physical processes come. This is because power sector has not adopted these technologies, but the chemical sector has actually developed these technologies for many years. Okay, so there are additional challenges in bringing it into the power sector for CO2 capture. Now that brings me to my slide, how to use gas hydrates to capture CO2. So basically, what are gas hydrates? Earlier, Amy spoke about gas hydrates. Also, Chung spoke about gas hydrates. So gas hydrates are basically made up of water and a gas molecule, right? So if you mix them together at a certain high pressure and a low temperature, you can form them. What you see in the slide is a naked eye view of a gas hydrates made in my lab. And what you see in the molecular view here is CO2 trapped in cage formed by water molecule. Now, basically, these are essentially there is no chemical reaction here. This is by weak van der Waals forces. So you can break it. They look exactly like ice. So you could actually, the same way as we melt ice, we could actually dissociate hydrates and take it out. So how do I apply this gas hydrates for CO2 capture? Again, this is driven by the thermodynamic aspects of the technology mover. There are about 70 different gas molecules that can sit into the hydrate cage, right? So that is what I would use but some molecules can go much faster into a certain cage and can also be readily occupied in certain cage. This is a fractionation effect, and that is the key driver for technology development. If you look at how we have applied CO2 hydrates as a technology enabler, this is how you do it. Let's say I take a fuel gas, which is the pre-combustion stream, or a flue gas. That's a topic I did my PhD on. In Singapore, I mainly work on fuel gas. So we take this fuel gas or flue gas, you mix it up with water at a certain pressure and temperature, you can form this white chunky mass. That's hydrate, right? So basically, CO2 partitions into the solid phase, whereas your residual gas phase is enriched with hydrogen or nitrogen. So that is where the fractionation effect happens. And then if you dissociate the CO2 hydrates that you have formed, you can actually recover all the captured gas and you can recycle back the water. So basically, hydrates consist of 85% water. So mainly the solvent that we use is water. That is the key advantage for us in this technology. And this CO2 gas can go for CO2 storage or utilization. I'm going to talk about CO2 storage as well later in my slide. Now, over the last 10 years, we have done quite a bit of innovation on this space. As Hans said, I'm not going to go into the technical details. What you see here is this is where we have reached in terms of capacities in the capture process. This is where our ideal capacities are. There is still room for further innovation, and that is what my lab is focusing on. Now, if you look at this part, there is a video here. Oops. We also focus on process innovation, and that is where we identify cheaper materials for operating this process in a packed bed column. And what you see there are the white popcorns that are popping out are CO2 hydrates when you pass through a fuel gas or a flue gas stream. Okay, And we also are looking at the process scale part of it. We are using temperature swing adsorption or pressure swing adsorption as our analogy to develop a technology. So as again, the TRL level is around 2.5. We are continuously improving this technology on that landscape. Now, if you look at CO2 sequestration, CO2 hydrates has a key role in CO2 sequestration. Earlier, Chung presented his conceptual views of forming CO2 hydrate. And that is where I'm going to press upon now. This is a project I work very closely with ExxonMobil, as highlighted by Adam as well. So there are several options of looking at CO2 sequestration. Hans presented many of those. I'm going to present a new concept, which is based on hydrates. So if you look at hydrates, nature provides you a queue. Nature has been storing methane in the form of hydrates for millions of years. So basically what you're trying to do is you're trying to take that as a queue and put CO2 into those places where water is readily available, right? So basically, learn from nature, lock CO2 in the solid phase is my message in this slide. There are a number of ways how you can lock CO2 in the form of hydrates. You could do that in the permafrost locations where you can inject CO2. And with the presence of water and the hydrostatic pressure, you can actually readily form hydrates. Or you could inject them in the deep ocean. Earlier, Chung presented a slide on that. When you inject them in deep ocean, you can form hydrates. Hydrates can also help in the aquifers injection, where it can form a seal if you could trigger the hydrate formation process. So this is the overall activity that's going on in the last 2 years with ExxonMobil. We are almost the first in the world to demonstrate that actually you can form hydrates in these oceanic sediments, and we have done tremendous work on that. Unfortunately, due to IP issues and confidentiality agreements, I'm not presenting that result. But however, the result is going to come out into the public domain very soon. We are actually summarizing this work in high impact journals as I speak. So if you look at the capacity wise, you could store a lot of CO2. If you look at what we have emitted in the last 10 years, it's around 400 gigatons of CO2. If we want to avoid a 2-degree scenario, we are looking at the need for 764 roughly gigatons of CO2 capacities. And the green ball here shows you the CO2 hydrate capacity for CO2 storage. How am I doing?
Three more minutes. 3 more minutes.
Perfect.
Thanks.
I'm on time. So if you look at this pyramid here, we have summarized a number of options of how CO2 can go in. The best ones are in the top part here, whereas the lower ones have extremely additional challenges coming into play. Okay, this is recently summarized in a publication which we have published in Energy and Fuels. Now, if you look at my lab's capability on CCS, in fact, I'm one of the best in the world in terms of gas hydrates, as was recently identified by a impact analysis study from UK. So basically, I have done quite a lot of work on the capture side. In the last 2 years, we have expanded that horizon with ExxonMobil on the sequestration or storage side. We have developed more than 24 researchers in Singapore, all of them scattered around industry as well as in academia. And we are highly visible on the impact scale, not on the productivity scale, more on the impact scale, if I may say. And we have capabilities on all of these aspects related to CCS. I'm very open to collaboration with our friends around Norway on this topic. If you look at my concluding remarks, the selective encapsulation of CO2 in hydrates can be employed for CO2 capture, be it flue gas or fuel gas, or even natural gas based power generation. There is a huge potential for long-term CO2 sequestration. So I would like to leave this slide with those 2 points in mind. And I would like to thank all my sponsors. In special here, I would like to thank ExxonMobil for working with us for the past 2 years on a very exciting idea, which is to store CO2 in the form of hydrates. That's my last slide. Thanks, everyone.
Thank you, Praveen, for a very good presentation. So actually, we have still a bit of time for some Q&A before some concluding remarks from me, Matteo, and Christian. So any questions from the floor? There is a question from Richard to Praveen about what is the energy footprint for the required high pressures and low temperatures to make CO2 hydrates?
That's a very good question, Richard. If you look at the capture side, we have done the energy analysis. The energy penalty based on a pre-combustion stream is around 25%. Okay. Now, what we have recently identified is if I couple this particular process, because I need low temperatures for forming hydrates, and if I couple it with an LNG utilization plant within Singapore, right, my energy penalty is less than 10%. So this is a very exciting prospect that we are going to move into in the near future. So the energy penalty is roughly around 25%. As Matteo said, you need 25% more energy to capture the CO2. And if you look at the benchmark for amine-based, it's around 18 to 20%, I would say, the best in class. Yeah.
Thanks, Praveen. Actually, one question also from the floor. The question is by Andrew Bedford to Hans is about how microbes basically are going to impact, how is going to the microbes contaminants are going to impact have an impact on the gas feedstock. I know you replied in the chat. Maybe you want to share with the rest of the audience.
Yeah, it depends on the contaminant, and different feedstocks have different contaminants. The big one that we have to work with is H2S, which is also corrosive, so it influences the entire process. Fortunately, it can be scrubbed quite easily. But there's other opportunities here, because as you know, microbes are evolved to strip energy and carbon from just about everything on the planet. So you can always think about a way of engineering a new biotech, a new engineered community to deal with that contaminant, and perhaps there's a benefit in that as well.
Thank you, Hans.
There is a question by Zidong. Actually, Alessandro, there is a question by Leong Zidong, if I may take it in the chat window. What are the open problems related to TRL? That's a very good question. If you look at CO2 storage, right, there is no limitations in TRL, because with ExxonMobil, what we are trying to do is, for the first time in the world, a proof of concept that demonstrate long-term stability, as well as the first proof that hydrates will remain stable. I mean, the time scale is still small. We are now focusing on possibly doing some modeling to project them for, let's say, a 50-year, 100-year, or 300-year cycle. So there is no limitation with regards to TRL or hydrates as a storage technology. Whereas for the capture technology, you must understand Singapore's landscape is very different. 95% of our energy is from natural gas. The CO2 stream in the exhaust is typically 5%. So from a chemical engineer point of view, you have to put more energy to take 5% into 90%. So what Singapore should look at is, rather taking it to 90%, can we take it to a higher percentage? Could be 30, could be 40, but then what you do downstream, what you do with that should also be factored into consideration. So that's the key challenge here. It's not just the TRL level for any CO2 capture, but the energy penalty of moving something from 5% to 90% is a killer in terms of technology deployment. Yeah.
Thank you, Praveen. Any further question from the floor? Matteo, you're on mute. Yeah.
Yeah. Probably I would like to ask Richard on his opinion from a thermodynamic perspective. I mean, we've seen the hydride route. We've seen the route that Hans Christopher is proposing, and these are Praveen is telling that the TRL of the hydrate is quite high already, but nevertheless, these are different way of utilizing and storing. And how would you put into your chart of that you presented in terms of availability of how to use that CO2, Richard?
Well, I'm not quite sure I understand in your ability to use the CO2.
So no. What I was you said that going for CO2, putting energy into the system, for example, with hydrogen being a green, being a gray, or being blue, provides allow us to go to either biofuels and whatever else. And you've given an idea of the TRL of these different technology, for example, of methanol production. So have you considered, for example, the bioengineering, and would that how do you consider into your? I mean, have you looked at it? Have you thought of it?
Well, I mean, of course, interesting, and biomass essentially is just already, biological CO2 sequestration. It's so there is a lot to be said for the microbe aspect for utilizing CO2. The question is, I don't know what the life cycle analysis is with respect to using those sorts of technologies versus traditional technology. I know that photosynthesis is a notoriously ineffective process. But I don't have the answers to those questions.
Hans-Christopher, you probably can help us out understanding a bit better. So if I need to gene manipulate a species in order to get more CO2, that specific plant or whatever needs to grow. So it needs a time to get there. Could I provide biophages, gene manipulated virus that attack just biological bacteria to encode a different way of getting CO2? And could you illuminate us, depending on how far have we gone on the things that you are proposing? Are we still on the very basic research side, if I understand it correctly?
Yeah, I think I have two comments. Technology is a major unknown for the innovation process here. The rate at which it's moving and the amount of things we're discovering in the genome of the world provides a lot of opportunity. There are thermodynamic limitations on what photosynthesis can do, but our ability to customize the production of biomass and biomolecules will also let us access new markets. So high value compounds such as phytopigments for nutraceuticals, which can help the economics of CCU or CCS. Mm-hmm. How far have we gone? Probably the most promising technologies are gas fermentation with microbes and algal CCU. And they're at the pre-industrial or small-scale industrial stage. I think there is no time to wait for synthetic biology to change the world, although undoubtedly it will. The role it has to play in CCSU is still a little unclear, but we should keep an open mind.
Just one comment. I appreciate the idea that you're making high-value materials, but those are by definition going to have a small market. So the amount of the CO2 that you actually are utilizing is relatively limited.
Yes, but that just offsets the cost for other processes. So, for instance, biomass itself, like we started in biofuels with the algae movement, and it was really clear many companies got started and that they weren't going to turn a profit. But then most of the companies that stayed in business are now producing high-value compounds, nutraceuticals, isoprenoids for rubbers and things like that. And so that's what supports the economics, and somebody has to pay for this somewhere.
Yeah, but
I agree with you there.
Yeah, but Hans-Christopher, what I think is that this is definitely something that goes into added value of this carbon, but at the same time, this is just one of the toolkits, one of the technology that needs to be put in place if we really want to achieve any type of result. But I'm going to leave the floor to Alessandro, but originally we were thinking of summarizing some of the view that was presenting. I mean, unfortunately, there is no much time for discussion, and but in a form of a white paper or a disseminating material that present this type of opinion. And we've on enhanced oil recovery, in which type of context these can be considered as a storage type of technology, and the reduction of the footprint of oil production, and therefore a role. So would it be a possible idea to sort of, as a follow-up of this webinar, to write up 5, 6, 7 questions, and each of us can give a bit of an answer of these questions. I mean, few of them, all of them, or whatever, in a couple of pages. And then Alessandro and I will try to put it together and merge it into a coherent story. It's not going to be easy, but that's also dependent on how well and how focused these questions are going to be posed. And this is, again, up to the fact on whether you guys are interested or not. Nice talk.
Thank you.
I would like.
I mean, the past few weeks. So I think we are running out of time. I mean, I just wanted to say a few concluding remarks. I would like to thank all the speakers. It was a very interesting session. We had a bit of different overviews from industry, research, more fundamentals, more applied. So I think it was very interesting. I learned a lot myself. And yes, I would like to pass the floor to Per Christer actually for the concluding remarks about this session. Thank you, everybody.
Yeah, thank you. I just have to, I will second that, Alessandro and Matteo. And Matteo, thank you for being hands-on with follow-up activities. That's you in a nutshell. So definitely let's look at some problem statements. Let's see where we can collaborate. I think there is a lot of common interest in this. I'm very on Prof's initiative around the Southern Star initiative, and I know that there are many Norwegian stakeholders that are that could be very supportive of this. Everything from CO2 transport, land CO2 transport. We have several shipping companies that would be very interested in looking into concepts for transport of cryogen gases. The hydrate element, Prof. Linga, is definitely something we have to. We have discussion on today as well on a different aspect, and that was more of using the cold from LNG. We haven't touched into that today, but there are elements there that we should follow up on. The CCUS is a I think we could spend several days on discussing that back and forth, where the opportunities and the chances are. But definitely Singapore is moving forward with its strategies and its plans within this space, within the decarbonization space as general, not only in the CCUS but also on hydrogen that we should discuss tomorrow. And the energy efficiency that was discussed yesterday. So I really see that there are many overlapping interests. There are many commonalities. There's also complementarities between the leading universities and research institutions in Singapore and Norway. So to just copy Matteo's last comment as well, let's put up a list of interesting areas, problem statements or missions, as they are popularly called here, and take them further. So with that, I would like to thank everybody for a great webinar. Thanks to Matteo and Alessandro for a great co-chairing. To see many of you tomorrow at the hydrogen webinar. Same place, almost same URL, I think. And then with that, have a nice, very nice evening or morning. And Prof. Lau, don't talk to strangers today. There will be a lot of riots in Texas tomorrow and the day after tomorrow.
No riot.
Take care. Take care.
Okay, guys.
Bye. Have a good day.
Thanks. Okay.
Thank you.
Bye
Bye.
now. Bye
Bye.
now.